Black holes are among the most extreme predictions of modern physics. Although they emit no light, their gravity profoundly influences stars, gas, and even entire galaxies. They occupy regions of space-time that can be arbitrarily small while containing masses millions or billions of times greater than the Sun. They represent the final state of massive stellar collapse and may probe physical laws beyond current theory. Once dismissed as purely mathematical solutions to Einstein's equations, black holes are now directly supported by observation. Their shadows have been imaged, their mergers detected through gravitational waves, and their presence inferred from precise measurements of orbital motion and high-energy radiation. Black holes are not uniform objects. They differ in mass, spin, origin, and environment. Some rotate near the theoretical maximum allowed by general relativity, while others rotate slowly. Some formed from recent stellar deaths, while others may trace back to the earliest moments of the universe. Understanding this diversity begins with the simplest and most well-defined black hole in theoretical physics. Schwarzschild black holes. In 1916, just months after Einstein published his theory of general relativity, a German physicist named Karl Schwarzschild did something remarkable. He was serving on the Russian front during World War I, far from any university or laboratory, yet he managed to solve Einstein's equations exactly. What he found was the first mathematical description of a black hole, an object so simple in structure that it would become the blueprint for understanding all others. Today, we call it a Schwarzschild black hole, and it remains the purest form of gravitational collapse. A Schwarzschild black hole is defined by a single property, mass. It does not rotate, it carries no electric charge. It simply exists as a spherical warp in space-time, pulling everything toward its center with relentless inevitability. Imagine taking the Sun and compressing it down to a sphere just 6 kilometers across. The result would be a Schwarzschild black hole with one solar mass. The surface of this sphere, the point of no return, is called the event horizon. Cross it, and you are lost forever. Not because the black hole is pulling harder once you cross, but because space-time itself has bent so severely that all paths now lead inward. There is no direction you can move, no speed you can achieve, that points away from the center. The mathematics of Schwarzschild black holes are elegant and unforgiving. The event horizon radius, known as the Schwarzschild radius, is determined entirely by mass. For our Sun, that radius would be 3 kilometers. For Earth, it would be just 9 millimeters. That means if you could somehow compress our entire planet into a sphere the size of a marble, it would collapse into a black hole. The formula is simple. The radius grows linearly with mass. Double the mass, double the radius. A black hole with 10 solar masses has an event horizon roughly 60 kilometers across. One with 1 million solar masses would span nearly 3 million kilometers, larger than our Sun itself. But here's where things get strange. The event horizon is not a physical surface. There is no wall, no barrier, no membrane. If you were falling toward a Schwarzschild black hole, you would not feel anything special as you crossed the horizon. Locally, space-time would seem smooth and continuous. You would not even know you had passed the point of no return until you tried to turn around and realized you could not. From your perspective, time would continue normally. But to an outside observer watching you fall, something entirely different would happen. They would see you slow down as you approached the horizon, your movements becoming more and more sluggish. The light from your body would redshift, stretching toward longer and longer wavelengths until you faded into darkness. They would never actually see you cross. To them, you would appear frozen at the edge forever, a ghost image preserved for eternity. This is the bizarre effect of gravitational time dilation. Near the event horizon, time itself slows down relative to distant observers. Clocks tick slower, processes unfold in slow motion. If you could somehow hover just above the horizon for 1 hour, decades or even centuries might pass in the outside universe. This is not science fiction. This is the direct consequence of Einstein's equations, and it has been confirmed by countless experiments and observations. GPS satellites, for instance, must account for time dilation caused by Earth's gravity. Near a black hole, the effect is simply taken to its extreme. Inside the event horizon lies the true mystery. According to Schwarzschild's solution, all the mass of the black hole is concentrated at a single point called the singularity. This is where density becomes infinite and space-time curvature becomes infinite. Our current theories break down completely here. General relativity cannot tell us what happens at the singularity because the equations produce nonsensical results, infinities that suggest the theory itself is incomplete. Most physicists believe that quantum mechanics, the science of the very small, must eventually replace general relativity at this scale. But we do not yet have a working theory of quantum gravity, so the singularity remains a placeholder for our ignorance. Schwarzschild black holes, despite being the simplest type, are also the rarest in nature. Why? Because in the real universe, nothing is perfectly still. Stars rotate. Gas clouds swirl. When a massive star collapses, it carries its angular momentum with it, and that spin does not simply disappear. As a result, most black holes in nature are rotating, not static. But the Schwarzschild solution remains invaluable because it provides the foundation. It is the baseline case, the reference point against which all other black holes are measured. When astronomers detect a black hole candidate, one of the first questions they ask is, how close is it to a Schwarzschild black hole? How much does it deviate from the ideal? These objects also give us insight into the geometry of space-time itself. Around a Schwarzschild black hole, space is curved in ways that defy everyday intuition. Light bends as it passes nearby, a phenomenon called gravitational lensing. If you could orbit close to the event horizon and look outward, you would see the entire universe compressed into a shrinking circle of light above you. Behind you, below you to your sides, there would be only darkness. The black hole would warp the light from distant stars so severely that the sky itself would seem to collapse inward. Another peculiar feature is the photon sphere, a region located 1.5 times the Schwarzschild radius from the center. At this distance, light itself can orbit the black hole. Photons traveling tangentially at this altitude will circle endlessly, trapped in a loop. If you were standing at this distance and looked carefully, you might even see the back of your own head as light from your body completed a full orbit around the black hole. This is not a stable orbit, though. The slightest nudge inward and the photons fall toward the event horizon. The slightest nudge outward and they escape to infinity. Schwarzschild black holes are also perfect laboratories for thought experiments. Physicists use them to test ideas about information, entropy, and the nature of space-time itself. One of the most famous puzzles in modern physics, the black hole information paradox, begins with Schwarzschild geometry. If you throw a book into a black hole, where does the information in that book go? Does it disappear forever, violating the laws of quantum mechanics? Or is it somehow preserved, encoded on the event horizon, or released in Hawking radiation? These questions remain unanswered, and they strike at the heart of our understanding of reality. In the end, Schwarzschild black holes are both the simplest and the most profound. They are the ghosts of collapsed stars, stripped of all features except mass. They are the clearest windows we have into the warping of space-time, the slowing of time, and the breakdown of our theories. And while they may be rare in the cosmos, their influence on physics is immeasurable. They taught us that black holes are real, that Einstein was right, and that the universe is far stranger than we ever imagined. Kerr black holes. If Schwarzschild black holes are the calm, motionless cause of gravitational collapse, then Kerr black holes are their wild, spinning cousins. In 1963, New Zealand mathematician Roy Kerr solved Einstein's field equations for a rotating black hole, and what he discovered changed everything. Real black holes, it turns out, are almost never stationary. They spin, sometimes at astonishing speeds, and that spin introduces effects so bizarre they challenge our deepest intuitions about space and time. A Kerr black hole is defined by two properties: mass and angular momentum. The more it spins, the more it drags spacetime around with it, creating a whirlpool effect that extends far beyond the event horizon. This phenomenon is called frame dragging, and it means that nothing near a Kerr black hole can remain still. Even light itself is forced to spiral as spacetime itself rotates. Imagine standing in a river where the current is so strong that no matter how hard you swim against it, you are pulled downstream. That is what frame dragging does to spacetime. Near a rapidly spinning black hole, you cannot orbit in the opposite direction of its spin. The current of spacetime itself forces you to move with the rotation. The event horizon of a Kerr black hole is no longer a perfect sphere. Instead, it bulges at the equator and flattens at the poles, shaped like an oblate spheroid. The faster the black hole spins, the more pronounced this distortion becomes. In fact, there is a theoretical maximum rotation speed, a limit where the black hole spins so fast that the event horizon nearly disappears. Physicists call this an extremal Kerr black hole, and it represents the edge of what is physically possible. If a black hole were to spin any faster, the singularity at its core would be exposed to the outside universe, creating what is known as a naked singularity. Most scientists believe this cannot happen, a principle called cosmic censorship, but proving it remains one of the great challenges of theoretical physics. One of the strangest features of a Kerr black hole is the ergosphere, a region outside the event horizon, where spacetime is dragged so violently that nothing can stay still. This region extends outward from the event horizon, especially near the equator, and it has a remarkable property. You can enter the ergosphere and still escape, something impossible once you cross the event horizon of any black hole. But while you are inside, you cannot simply hover in place. You must move, swept along by the rotation of spacetime itself. This creates an incredible opportunity known as the Penrose process, named after physicist Roger Penrose. In theory, you could enter the ergosphere, drop an object into the black hole, and extract energy in the process. The object you drop would carry negative energy relative to the outside universe, and you would emerge with more energy than you entered with. In essence, you could steal rotational energy from the black hole itself. This is not just theoretical speculation. Astrophysicists believe the Penrose process might explain some of the most energetic phenomena in the universe. When matter falls into a spinning black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees. The intense magnetic fields threading through this disk can tap into the black hole's rotation, launching powerful jets of particles and radiation at nearly the speed of light. These jets can extend for thousands of light years, visible across the cosmos. Some of the brightest objects in the universe, quasars and active galactic nuclei, are powered by spinning black holes feeding on vast amounts of matter. The energy does not come from the matter itself, but from the spin of the black hole, extracted through the interplay of magnetic fields and frame dragging. Inside a Kerr black hole, things get even stranger. Unlike a Schwarzschild black hole, which has a single point singularity, a Kerr black hole has a ring singularity. This is a one-dimensional loop, infinitely thin, spinning around the axis of rotation. In principle, you could pass through the center of this ring without hitting the singularity itself. What lies beyond is a subject of pure speculation. Some solutions to Einstein's equations suggest that passing through a ring singularity could lead to other regions of spacetime, perhaps even other universes. These solutions also hint at the existence of closed time-like curves, paths through spacetime that loop back on themselves, theoretically allowing time travel. Before you get too excited, though, these solutions are likely unphysical. Most scientists believe that quantum effects, not yet fully understood, would prevent such exotic possibilities from occurring in reality. The spin of a Kerr black hole also affects how we observe it. When gas spirals inward toward the event horizon, it emits X-rays that carry information about the black hole's rotation. By studying the shape and motion of these X-ray emissions, astronomers can measure the spin of black holes millions of light years away. Some black holes spin slowly, at just a fraction of the maximum rate. Others, like the black hole in the galaxy, NGC 1365, spin at nearly 84% of the theoretical maximum. That means its equator is moving at a significant fraction of the speed of light, dragging space-time along with unimaginable force. Why do black holes spin at all? The answer lies in their formation. When a massive star collapses, it conserves angular momentum. If the star was rotating, even slowly, the collapse amplifies that spin. Imagine an ice skater pulling in their arms during a spin. They rotate faster because angular momentum is conserved. The same principle applies to black holes, but on a cosmic scale. A star rotating once every few days could collapse into a black hole spinning hundreds of times per second. Over time, as the black hole consumes more matter, its spin can increase or decrease depending on the direction from which the matter falls. If matter falls in aligned with the black hole's rotation, it speeds up. If it falls in from the opposite direction, it slows down. Kerr black holes are not just mathematical curiosities. They are the rule, not the exception. Nearly every black hole detected in the universe shows evidence of rotation, from stellar mass black holes formed in supernova explosions to supermassive black holes at the centers of galaxies. Spin is a fundamental property, and that spin has profound consequences. It shapes the environments around black holes, powers some of the most violent explosions in the cosmos, and may even hold clues to the nature of space-time itself. The existence of Kerr black holes also forces us to reconsider what we mean by emptiness. A Schwarzschild black hole is a static object, a frozen warp in space-time. But a Kerr black hole is dynamic. It churns, it drags, it radiates influence outward through frame dragging and magnetic fields. In a sense, it is not just an object but a process, a spinning vortex that reshapes everything around it. And because most black holes spin, the universe is filled not with still voids, but with whirlpools of space-time, each one a testament to the violent deaths of stars and the relentless grip of gravity. Stellar mass black holes. The universe does not create black holes gently. It forges them in the most violent events imaginable, the collapse of massive stars. These stellar mass black holes are the remnants of stars that lived fast and died explosively, leaving behind objects so dense that a teaspoon of their material would weigh billions of tons. They are the first type of black hole scientists ever confirmed, and they remain among the most common in the galaxy. To understand them, we have to understand how stars die. Not every star becomes a black hole. Our Sun, for example, will never undergo such a fate. It is simply too small. When it exhausts its nuclear fuel in about 5 billion years, it will shed its outer layers and leave behind a white dwarf, a hot, dense ember roughly the size of Earth. Stars like our Sun end quietly. But stars much more massive, those at least 20 times heavier than the Sun, meet a very different end. For most of their lives, these giants burn hydrogen and helium in their cores, fusing lighter elements into heavier ones. This fusion releases energy, and that energy creates an outward pressure that balances the inward pull of gravity. It is a delicate equilibrium, but eventually the fuel runs out. When a massive star exhausts its nuclear fuel, the core can no longer support itself against gravity. In less than a second, the core collapses. Electrons are crushed into protons, forming neutrons, and the core becomes incredibly dense. For a brief moment, it resembles a neutron star, an object so dense that a sugar cube of its material would weigh as much as a mountain. But if the core is too massive, even neutron degeneracy pressure cannot hold it up. Gravity wins. The core collapses past the neutron star threshold and shrinks without limit, forming a black hole. The outer layers of the star, meanwhile, rebound off the collapsing core and explode outward in a supernova, one of the brightest events in the universe. For a few weeks, a single dying star can outshine an entire galaxy. And at the center of that explosion, hidden beneath the debris, a stellar mass black hole is born. Stellar mass black holes typically weigh between 3 and 100 solar masses. The lower limit comes from physics. any object below about 3 solar masses will stabilize as a neutron star rather than collapsing into a black hole. The upper limit is less clear, but it is related to the maximum mass a star can have before it becomes unstable. The most massive stars lose so much mass through stellar winds that by the time they collapse, they rarely produce black holes heavier than a few dozen solar masses. However, recent discoveries have challenged this idea. In 2019, the LIGO and Virgo gravitational wave detectors picked up the collision of 2 black holes with a combined mass exceeding 100 solar masses. One of them weighed about 85 solar masses, far heavier than any black hole formed from a normal star should be. This has led scientists to propose new formation channels, such as black holes merging multiple times to grow beyond the usual limits. Finding stellar mass black holes is not easy. They emit no light, so we cannot see them directly. Instead, astronomers hunt for their effects on nearby objects. The most common method is to look for binary systems where a black hole orbits a visible companion star. As the black hole's gravity pulls gas from the companion, the gas spirals inward, forming an accretion disk. This disk heats up due to friction and intense compression, reaching temperatures of millions of degrees. At these temperatures, the gas emits X-rays, which telescopes can detect from Earth. By studying the X-ray emissions and the motion of the companion star, scientists can calculate the mass of the invisible object. If that mass exceeds 3 solar masses and shows no signs of a surface or magnetic field, the conclusion is clear. It is a black hole. One of the most famous examples is Cygnus X1, located about 6,000 light-years away in the constellation Cygnus. Discovered in the 1960s, it was one of the first black hole candidates ever identified. Cygnus X1 consists of a black hole roughly 21 times the mass of the Sun, locked in orbit with a blue supergiant star. The black hole is actively feeding, pulling gas from its companion and heating it to millions of degrees. The X-ray emissions are so strong that they were detected even with the limited instruments available in the 1960s. For years, there was debate about whether Cygnus X1 truly contained a black hole. Stephen Hawking famously bet against it, wagering that it would turn out to be something else. In 1990, as evidence mounted, he conceded the bet. Today, there is no doubt. Cygnus X1 is a black hole. Another landmark discovery came in 2015 when LIGO detected gravitational waves from 2 merging black holes. This was the first direct observation of gravitational waves, ripples in spacetime predicted by Einstein a century earlier. The 2 black holes, weighing 36 and 29 solar masses, spiraled into each other and merged, releasing more energy in a fraction of a second than all the stars in the visible universe combined. The event, designated GEW 150914, proved not only that gravitational waves exist, but also that binary black hole systems are real and that black holes can collide and merge. Since then, LIGO and Virgo have detected dozens of similar events, giving us a new way to study black holes across the universe. Astronomers now estimate that there are roughly 100 million stellar mass black holes in the Milky Way alone. Most of them are not feeding on companion stars, so they remain invisible. They drift silently through the galaxy, detectable only through gravitational lensing, or the rare occasions when they pass near another star. Some may wander alone for billions of years, never interacting with anything. Others grow over time, consuming gas or merging with other black holes. Each merger releases gravitational waves, sending signals across spacetime that we are only now learning to detect. Stellar mass black holes also play a role in shaping their environments. When a supernova explodes, it scatters heavy elements like carbon, oxygen, and iron into space. These elements are the building blocks of planets and life. Every atom of carbon in your body was forged in the core of a massive star and expelled in a supernova. The black hole left behind is a remnant of that process, a silent witness to the cycle of stellar birth and death. In this way, black holes are not just destroyers. They are part of the cosmic recycling system that enriches galaxies and makes life possible. The study of stellar mass black holes has also revealed unexpected diversity. Some spin rapidly, others slowly. Some are isolated, others in binaries. Some formed recently, others billions of years ago. By mapping their properties, astronomers are piecing together the history of star formation and evolution in our galaxy. Each black hole carries information about the star that formed it, the environment it was born in, and the journey it has taken through space. And with new instruments like the James Webb Space Telescope and the next generation of gravitational wave detectors, we are entering an era where we can study these objects in unprecedented detail. The story of stellar mass black holes is only beginning. Intermediate mass black holes. Between the stellar remnants weighing a few dozen suns and the monsters anchoring galaxies lies a puzzling gap. Logic suggests there should be black holes in this range, objects weighing hundreds or thousands of solar masses. These are called intermediate mass black holes, and they are among the most elusive objects in astronomy. For decades, scientists have searched for them, finding tantalizing hints but few definitive answers. Their existence, or lack thereof, could reveal how supermassive black holes grow and how galaxies evolve. The mystery begins with a simple question. How do you get from a stellar mass black hole to a supermassive one? A black hole formed from a collapsing star weighs at most 100 solar masses, but the supermassive black holes at the centers of galaxies weigh millions or even billions of times more. How did they grow so large? One possibility is that they started as intermediate mass black holes, objects that formed early in the universe and gradually accumulated mass over billions of years. Another possibility is that they formed directly from the collapse of massive gas clouds, bypassing the stellar stage altogether. Without finding intermediate mass black holes, it is hard to test these theories. Intermediate mass black holes are expected to weigh between 100 and 100,000 solar masses. That is large enough to distinguish them from stellar remnants, but small enough that they would not dominate the centers of large galaxies. Instead, they might hide in smaller galaxies, dense star clusters, or the outskirts of larger galaxies. The problem is that they are difficult to detect. They do not feed on as much matter as supermassive black holes, so they produce weaker X-ray and radio emissions. They are also smaller, so their gravitational influence extends over a smaller region. Finding them requires careful observation and a bit of luck. One of the best places to search is in globular clusters, ancient groups of stars packed tightly together. These clusters can contain hundreds of thousands of stars in a region just tens of light years across. If an intermediate mass black hole lurks at the center, it would influence the motions of the surrounding stars. By measuring how stars orbit the cluster's center, astronomers can infer the presence of a hidden mass. Several globular clusters have shown evidence of central black holes. One candidate is 47 Tucanae, a cluster located about 16,000 light-years from Earth. Observations suggest it may contain a black hole of at least 2,000 solar masses, though the evidence remains inconclusive. Another promising location is dwarf galaxies, small galaxies that orbit larger ones. Some dwarf galaxies appear to host black holes that are neither stellar nor supermassive, but fall squarely in the intermediate range. One example is the dwarf galaxy NGC 4395, which contains a black hole weighing around 300,000 solar masses. While this is on the upper end of the intermediate range, it still provides a valuable clue. If dwarf galaxies can harbor such black holes, it suggests that intermediate mass black holes may be more common than we think. The strongest evidence for intermediate mass black holes comes from X-ray observations. Occasionally, astronomers detect sudden flares of X-rays from distant galaxies, events known as ultraluminous X-ray sources, or ULX. These flares are too bright to be explained by stellar mass black holes, but too faint and erratic to come from supermassive ones. The most likely explanation is an intermediate mass black hole feeding on a nearby star. One well-studied example is HLX-1, located in the galaxy ESO 243, 49, about 300 million light-years away. Observations suggest it contains a black hole weighing around 20,000 solar masses, making it one of the best intermediate mass black hole candidates discovered so far. Gravitational waves offer another avenue for detection. When two intermediate mass black holes merge, they release gravitational waves with frequencies different from those produced by stellar mass or supermassive black hole mergers. The LIGO and Virgo detectors, which are optimized for stellar mass black holes, can potentially detect the most massive intermediate black hole mergers. In 2019, LIGO detected a merger involving a black hole weighing about 85 solar masses, one of the heaviest ever observed. While this is technically at the boundary between stellar and intermediate mass, it suggests that heavier black holes do exist and can be detected. Why are intermediate mass black holes so rare, or at least so hard to find? One possibility is that they do not form easily. Stellar black holes form from collapsing stars, and supermassive black holes likely form from massive gas clouds or the mergers of many smaller black holes. But what process would create something in between? One idea is runaway collisions in dense star clusters. If stars in a cluster collide and merge repeatedly, they could build up a massive star that eventually collapses into an intermediate mass black hole. Another idea is that intermediate mass black holes are the seeds of supermassive ones. They may have formed in the early universe and then grown over time by consuming gas and merging with other black holes. If this is true, then intermediate mass black holes may be rare today simply because most of them have already grown into supermassive ones. The discovery of intermediate mass black holes would have profound implications. It would fill in a critical gap in our understanding of black hole formation and growth. It would also help explain how supermassive black holes appeared so early in the universe. Observations show that massive black holes existed less than 1 billion years after the Big Bang, a puzzle known as the high redshift quasar problem. If intermediate mass black holes formed in the early universe, they could have provided the seeds that grew into supermassive ones much faster than stellar mass black holes alone could have. As telescopes and detectors improve, the search for intermediate mass black holes continues. The next generation of gravitational wave observatories, such as the Laser Interferometer Space Antenna, or LISA, will be able to detect mergers involving black holes in the intermediate mass range with much greater sensitivity. Space-based X-ray telescopes will also provide clearer views of distant galaxies, potentially revealing more ULX and hidden black holes. The James Webb Space Telescope, with its ability to peer into the early universe, may even spot the first intermediate mass black holes forming in ancient galaxies. For now, intermediate mass black holes remain one of the great mysteries of modern astrophysics. They are the missing link in the story of black holes, the bridge between stellar remnants and galactic giants. Finding them would not only complete the picture, but also unlock new insights into how the universe builds its largest structures. Supermassive black holes. At the heart of nearly every large galaxy lies a monster, not a creature of flesh and bone, but a gravitational beast so immense that it holds billions of stars in its thrall. These are supermassive black holes, objects that weigh millions or even billions of times the mass of the Sun. They are not just larger versions of stellar black holes. They are fundamentally different in scale, origin, and influence. And they play a central role in the life cycle of galaxies, shaping everything from star formation to the structure of the cosmic web itself. Our own Milky Way galaxy hosts a supermassive black hole at its center, known as Sagittarius A star. Located about 26,000 light-years from Earth, it weighs roughly 4 million solar masses. For most of human history, we had no idea it was there. The center of the galaxy is obscured by thick clouds of dust, blocking visible light. But in the 1990s, astronomers using infrared telescopes began tracking the motions of stars near the galactic center. What they saw was astonishing. Stars were orbiting an invisible point at breakneck speeds, some completing full orbits in just a few years. One star, designated S2, swings around the galactic center at speeds exceeding 5,000 kilometers per second, faster than most stars ever travel. The only explanation for such motion is a concentrated mass of extraordinary density, something with the gravitational pull of millions of suns crammed into a region smaller than the orbit of Mercury. That something is Sagittarius A star. In 2022, the Event Horizon Telescope captured the first direct image of Sagittarius A star. The image shows a glowing ring of hot gas surrounding a dark shadow, the silhouette of the black hole itself. This shadow is not the event horizon, but rather the photon sphere, the region where light orbits the black hole before either escaping or falling in. The image is remarkable not just for its beauty, but for what it confirms. The predictions of general relativity hold true even in the most extreme environments. The shape, size, and brightness of the ring match Einstein's equations almost perfectly. But Sagittarius A star is small compared to some supermassive black holes. The galaxy M87, located about 55 million light-years away, contains a black hole weighing 6.5 billion solar masses. Its event horizon spans about 40 billion kilometers, larger than the entire orbit of Pluto. In 2019, the Event Horizon Telescope captured an image of this giant as well, marking the first time humanity had ever photographed a black hole. The image shows a bright ring of gas and a dark central region, the shadow of an object so massive that it warps spacetime in visible ways. The energy released by matter falling into M87's black hole powers a jet of particles and radiation that extends for 5,000 light-years, shooting out from the galactic core at nearly the speed of light. How did such colossal objects form? This is one of the great unsolved questions in astrophysics. Stellar mass black holes form from collapsing stars, but even the most massive stars produce black holes of only a few dozen solar masses. To grow from that size to millions or billions of solar masses should take an extraordinarily long time. Yet observations reveal that supermassive black holes existed when the universe was less than 1 billion years old, far too early for them to have grown through normal processes. Several theories attempt to explain this mystery. One idea is that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe. Instead of forming stars first, these clouds collapsed directly into black holes weighing tens of thousands of solar masses, giving them a massive head start. Another theory suggests that dense clusters of stars in the early universe collided and merged repeatedly, forming massive stars that collapsed into intermediate mass black holes, which then merged to create supermassive ones. Supermassive black holes do not just sit passively at galactic centers, they actively shape their surroundings. When gas falls towards a supermassive black hole, it forms an accretion disk, a swirling structure heated to millions of degrees by friction and compression. The disk emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. In some cases, the energy is so great that it launches jets of particles at nearly the speed of light, beams that can extend for hundreds of thousands of light-years. These jets can plow through intergalactic gas, heating it and preventing it from collapsing to form new stars. In this way, supermassive black holes regulate star formation in their host galaxies, acting as cosmic thermostats that control how and when new stars are born. This relationship between black holes and galaxies is so tight that astronomers have discovered a correlation between the mass of a supermassive black hole and the mass of the galactic bulge, the central region of stars surrounding it. Galaxies with larger bulges tend to have more massive black holes. This suggests that black holes and galaxies grow together, influencing each other over cosmic time. The exact mechanism is still debated, but it likely involves feedback loops where the black hole's energy output affects the galaxy, and the galaxy's supply of gas affects the black hole's growth. One of the most extreme manifestations of supermassive black holes is the quasar. A quasar is a supermassive black hole actively feeding on enormous amounts of matter, shining so brightly that it can outshine its entire host galaxy. Quasars are among the most luminous objects in the universe, visible across billions of light-years. They were most common in the early universe when galaxies were forming and merging frequently, providing a steady supply of gas to feed their central black holes. Today, quasars are rarer, but they provide a window into the violent processes that shaped young galaxies. Some supermassive black holes are even more exotic. In 2021, astronomers discovered a black hole in the galaxy M87 that appears to be wobbling. This wobble, called precession, is caused by the black hole's spin and the warping of spacetime around it. Over time, the axis of the black hole's rotation slowly shifts, dragging the surrounding accretion disk and jets along with it. Observations over several decades have confirmed this wobbling motion, providing direct evidence of frame dragging, the same effect predicted for Kerr black holes. Another remarkable discovery is the existence of wandering supermassive black holes. When two galaxies merge, their central black holes eventually sink toward the center of the newly formed galaxy and begin to orbit each other. This process can take millions of years, and during that time, the black holes act as a binary pair. Eventually, they merge, releasing a burst of gravitational waves so powerful that it can recoil the combined black hole, kicking it out of the galactic center entirely. These recoiling black holes can wander through their host galaxies or even escape into intergalactic space. While rare, a few candidates have been identified, and their study could reveal how galaxy mergers and black hole dynamics interact. Supermassive black holes are not just astrophysical curiosities. They are fundamental to the structure and evolution of the universe. Without them, galaxies would look very different, perhaps forming stars too quickly and burning out in a few billion years. The energy released by feeding black holes regulates galaxy growth, controls star formation, and enriches the intergalactic medium with metals and energy. They are the architects of cosmic structure, the invisible hands that shaped the universe we see today. Primordial black holes. What if some black holes are older than stars, older than galaxies, older than anything else in the universe except the fabric of space-time itself? This is the idea behind primordial black holes, hypothetical objects that may have formed in the chaotic first moments after the Big Bang. Unlike every other type of black hole we have discussed, primordial black holes would not be the remnants of collapsed stars or the products of galactic evolution. They would be fossils from the birth of the universe, relics of a time when physics operated under conditions we can barely imagine. The early universe was unimaginably dense and hot. In the first fraction of a second after the Big Bang, all of space was filled with a roiling soup of energy and particles, fluctuating wildly as quantum mechanics and gravity battled for control. According to some theories, regions of slightly higher density could have collapsed under their own gravity before the universe had time to expand and smooth itself out. These collapses would have happened incredibly fast, within the first second of cosmic time, creating black holes directly from the primordial fireball. No stars, no supernovae, just pure gravitational collapse driven by the extreme conditions of the infant universe. What makes primordial black holes so intriguing is their potential size range. Unlike stellar or supermassive black holes, which are constrained by the physics of stars and galaxies, primordial black holes could theoretically have any mass. Some might be incredibly small, weighing no more than a grain of sand but compressed to the size of a proton. Others could be as massive as asteroids, planets, or even stars, all packed into volumes smaller than atoms. The smallest ones would have evaporated long ago through Hawking radiation, a quantum process where black holes slowly lose mass by emitting particles. But black holes above a certain threshold, roughly the mass of a small asteroid, would still exist today, drifting invisibly through the cosmos. This brings us to one of the most exciting possibilities: primordial black holes as dark matter. For decades, astronomers have known that the universe contains far more mass than we can see. Galaxies rotate too fast. Galaxy clusters are held together by more gravity than their visible matter can account for. Something invisible, something that interacts only through gravity, must make up about 85% of the matter in the universe. We call it dark matter, but we do not know what it is. particle physicists have proposed exotic particles like WIMPs and axions, but despite years of searching, none have been detected. Primordial black holes offer an alternative. What if dark matter is not made of particles at all, but of countless ancient black holes scattered throughout space? The idea is appealing for several reasons. Black holes are invisible, interacting only through gravity, exactly like dark matter. They are stable and long-lived, and unlike exotic particles, they do not require new physics beyond general relativity. If the early universe produced enough primordial black holes in the right mass range, they could account for all the dark matter we observe. Some estimates suggest that billions of primordial black holes could be passing through the solar system at any given time, completely unnoticed. They would be too small to affect planetary orbits and too diffuse to cluster visibly, but their combined gravitational influence would shape the motion of galaxies. However, the evidence is far from conclusive. Astronomers have placed strict limits on how many primordial black holes can exist in certain mass ranges. For example, if there were too many primordial black holes with masses similar to planets or stars, they would distort the light from distant stars through gravitational lensing more often than we observe. Similarly, if primordial black holes made up all of dark matter, they would affect the cosmic microwave background radiation, the faint glow left over from the Big Bang. So far, observations have ruled out primordial black holes as the sole explanation for dark matter in many mass ranges, but a window remains open. Black holes in the range of tens to hundreds of solar masses, or very small black holes near the mass of asteroids, could still account for a significant fraction of dark matter. One of the most tantalizing hints comes from gravitational wave detections. LIGO and Virgo have observed dozens of black hole mergers, and some of these black holes fall into a mass range that is difficult to explain with normal stellar evolution. For instance, black holes weighing around 30 solar masses are more common in LIGO data than expected from star collapse models. Could some of these be primordial black holes rather than stellar remnants? If primordial black holes formed in the early universe, they would have had billions of years to drift through space, occasionally encountering each other and merging. These mergers would produce gravitational waves indistinguishable from those of stellar black hole mergers, making it difficult to tell them apart. However, subtle differences in their spin distributions and clustering might eventually reveal their primordial origins. Another way to search for primordial black holes is through their effects on stars and planetary systems. If a primordial black hole passed through a star, it could disrupt the star's internal structure, potentially triggering unusual flares or oscillations. If one passed near a planet, it could perturb the planet's orbit, or even capture it, ejecting it from its solar system. While such events would be rare, they might leave detectable signatures. Astronomers are beginning to search stellar surveys and planetary data for anomalies that could hint at primordial black hole encounters. Primordial black holes also offer a potential explanation for another mystery: the existence of supermassive black holes in the early universe. Observations show that black holes weighing billions of solar masses existed less than a billion years after the Big Bang. Growing such massive black holes from stellar remnants in such a short time is difficult, but if primordial black holes provided the seeds, the problem becomes more manageable. A primordial black hole weighing thousands or even millions of solar masses could have formed directly from collapsing gas clouds in the early universe, then grown quickly by accreting surrounding matter. This would explain how supermassive black holes appeared so early without requiring exotic physics. Despite their appeal, primordial black holes remain hypothetical. No primordial black hole has ever been definitively detected. The best we have are tantalizing hints and open questions. But that is precisely what makes them so exciting. They sit at the intersection of cosmology, particle physics, and black hole physics, challenging us to think about the universe's earliest moments and its most mysterious components. If they exist, they would transform our understanding of dark matter, galaxy formation, and the history of the cosmos. And if they do not, ruling them out would still teach us valuable lessons about the limits of black hole formation and the conditions in the early universe. For now, the search continues. New telescopes, gravitational wave detectors, and computational models are pushing the boundaries of what we can observe and predict. Each new discovery, whether it supports or refutes the existence of primordial black holes, brings us closer to understanding the full spectrum of black holes and the role they play in the universe's grand story. Quantum black holes. At the opposite end of the size spectrum from supermassive black holes lie objects so small they challenge the very definition of what a black hole is. These are quantum black holes, also known as micro-black holes or Planck-scale black holes, and they exist at the frontier where general relativity and quantum mechanics collide. If they exist at all, they would be smaller than atoms, perhaps smaller than protons, yet still possess the defining feature of a black hole, an event horizon from which nothing can escape. They are the ultimate test case for theories of quantum gravity, and their properties defy everyday intuition. The concept of quantum black holes begins with a simple question: how small can a black hole be? According to general relativity, you can create a black hole by compressing any amount of mass into a small enough volume. Compress the Earth to the size of a marble, and it becomes a black hole. Compress a mountain to the size of a proton, same result. In principle, there is no lower limit. You could create a black hole with the mass of a grain of sand, a bacterium, or even a single atom, as long as you squeeze it into a region smaller than its Schwarzschild radius. For very small masses, that radius becomes incredibly tiny, approaching what physicists call the Planck length, about 10 to the negative 35 meters. This is the scale where quantum mechanics and gravity become equally important, and where our current theories begin to break down. At this scale, black holes would behave very differently from their larger cousins. For one, they would not last long. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. Due to quantum effects near the event horizon, they emit radiation, now known as Hawking radiation. This radiation carries energy away from the black hole, causing it to lose mass over time. For large black holes, this process is incredibly slow. A black hole with the mass of the Sun would take longer than the current age of the universe to evaporate, but for small black holes, the evaporation is rapid. A black hole with the mass of a mountain would evaporate in less than a second, releasing a burst of energy equivalent to millions of nuclear bombs. A black hole the size of a proton would vanish almost instantly, perhaps in a fraction of a trillionth of a second. This raises a fascinating possibility. Could quantum black holes be created in high-energy collisions? When particles smash together at extremely high speeds, such as in the Large Hadron Collider, they concentrate enormous energy into a tiny region. If that energy density is high enough, could it briefly create a micro-black hole? Some theories of extra dimensions suggest this might be possible. In these theories, gravity is much stronger at very small scales than we observe, because it leaks into hidden dimensions that we cannot see. If true, the energy required to create a quantum black hole would be lower than expected, potentially within reach of particle accelerators. Before you worry about the LHC swallowing the Earth, rest assured, even if micro-black holes were created, they would evaporate instantly through Hawking radiation, releasing their energy as harmless particles. Experiments at the LHC have searched for evidence of micro-black holes by looking for unusual patterns in particle collisions, but so far none have been found. Even without particle accelerators, the early universe may have been a natural factory for quantum black holes. In the first moments after the Big Bang, temperatures and densities were so extreme that quantum fluctuations could have spontaneously created tiny black holes. Unlike primordial black holes, which formed from larger scale density fluctuations, quantum black holes would have formed at the Planck scale, where spacetime itself becomes grainy and uncertain. Most of these would have evaporated immediately, but they could have left subtle imprints on the structure of the universe, effects that might be detectable in the cosmic microwave background or in the distribution of matter today. Quantum black holes also play a crucial role in theoretical physics. They are the testing ground for theories of quantum gravity, the long-sought framework that would unify general relativity and quantum mechanics. One of the biggest challenges in physics is understanding what happens at the singularity inside a black hole. General relativity predicts that density becomes infinite, but infinity is not a physical answer. It is a sign that the theory has reached its limits. Quantum mechanics should take over at this scale, but we do not yet have a complete theory that describes how. Quantum black holes, existing right at the boundary between the two theories, could provide crucial clues. If we could study them, even indirectly, we might learn how to build a unified theory of everything. Another puzzle is the black hole information paradox. According to quantum mechanics, information cannot be destroyed. But if you throw a book into a black hole, where does the information in that book go? Hawking radiation is thermal, meaning it carries no information about what fell into the black hole. This seems to violate quantum mechanics. The paradox is most acute for small black holes, which evaporate quickly. If a quantum black hole forms and evaporates in a fraction of a second, what happens to the information it swallowed? Physicists have proposed various solutions, from encoding information on the event horizon to suggesting that information escapes through subtle correlations in Hawking radiation. Quantum black holes, if they exist and can be studied, might help resolve this paradox. There is also the possibility that quantum black holes are connected to the fabric of spacetime itself. Some theories suggest that at the Planck scale, spacetime is not smooth, but rather a seething foam of virtual black holes constantly forming and evaporating. This quantum foam would be the underlying structure of reality, with particles and forces emerging from the collective behavior of countless micro-black holes. If true, quantum black holes are not rare exotic objects, but the fundamental building blocks of the universe. We would be living in a cosmos where space-time itself is made of black holes, constantly flickering in and out of existence at scales far too small to observe directly. Despite their theoretical importance, quantum black holes remain entirely hypothetical. We have no direct evidence that they exist, and detecting them would be extraordinarily difficult. Their tiny size and short lifetimes make them almost impossible to observe with current technology. Even if we created one in a particle accelerator, it would vanish before we could measure it. The best we can hope for are indirect effects, subtle anomalies in high-energy experiments, or cosmological data that hint at their presence. But the search is worthwhile. Quantum black holes represent the ultimate frontier of black hole physics, the place where our understanding of gravity, space, and time meets its deepest challenges. Binary black holes. Black holes are often portrayed as solitary objects, lone predators drifting through the cosmos. But the universe has a way of bringing things together, and black holes are no exception. Binary black holes, pairs of black holes locked in mutual orbit, are not only real but surprisingly common. When these pairs spiral together and merge, they create some of the most violent and energetic events in the universe, releasing more power in a fraction of a second than all the stars in the observable universe combined. And thanks to gravitational wave astronomy, we are now witnessing these cosmic collisions in real time. The story of binary black holes begins with binary stars. Many stars, perhaps most, are born in pairs or groups rather than in isolation. If both stars in a binary system are massive enough, both will eventually collapse into black holes. When this happens, you end up with a binary black hole system, two black holes orbiting each other, bound by gravity. These systems can persist for billions of years, slowly losing energy as they emit gravitational waves, ripples in the fabric of space-time predicted by Einstein a century ago. As the black holes lose energy, their orbits shrink. They spiral closer and closer, orbiting faster and faster, until finally, they collide and merge into a single larger black hole. The merger itself is a cataclysmic event. In the final moments before collision, the two black holes are orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. The immense acceleration produces gravitational waves so strong that they shake spacetime itself, stretching and compressing space in alternating waves. These waves propagate outward at the speed of light, carrying energy away from the system. When the black holes finally merge, the resulting black hole rings like a bell, settling down into a stable configuration. The entire process, from the final in-spiral to the ring down, takes less than a second. But in that brief moment, the system can release more energy than all the stars in the visible universe emit over the same time period. On September 14, 2015, humanity detected gravitational waves for the first time. The signal, designated GW150914, came from two black holes weighing 36 and 29 solar masses, located about 1.3 billion light-years away. They had been spiraling toward each other for millions of years, and in the final fraction of a second they merged, forming a black hole of 62 solar masses. The missing 3 solar masses were converted entirely into gravitational wave energy, radiating outward across the universe. When those waves reached Earth, they stretched and compressed space by less than 1,000th the diameter of a proton, a distortion so tiny it seems impossible to measure. Yet the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected it. The discovery confirmed Einstein's predictions, proved that binary black holes exist, and opened an entirely new way of observing the universe. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of binary black hole mergers. Each one provides a wealth of information. By analyzing the gravitational wave signal, scientists can determine the masses of the black holes, their spins, the distance to the system, and even details about their final orbits. These observations have revealed that binary black holes come in a wide variety of configurations. Some pairs have similar masses, others are highly asymmetric. Some black holes spin rapidly, others slowly. Some spins are aligned with the orbital motion, others are tilted or even opposite. One of the most surprising discoveries is that some black holes are heavier than expected. Stellar evolution models predict that black holes formed from collapsing stars should not exceed about 45 solar masses due to a process called pair instability, where very massive stars explode completely rather than leaving a remnant. Yet LIGO has detected black holes weighing 50, 60, even 85 solar masses. How did they get so big? One possibility is that they formed through previous mergers. A black hole that started at 30 solar masses could merge with another, growing to 60, then merge again, growing to 90. These hierarchical mergers might explain the heaviest black holes in the LIGO data, and they suggest that black holes can grow over time through repeated collisions. Binary black holes are not always isolated. Some form in dense environments like star clusters, where hundreds of thousands of stars and black holes are packed into a small region. In such environments, black holes can encounter each other dynamically, captured by gravity into temporary orbits that eventually lead to mergers. These dynamical captures produce binary black holes with different properties than those formed from binary stars, including more random spin orientations. By studying the population of binary black holes, astronomers can learn about the environments where they formed and the history of star formation in the universe. Another intriguing possibility is the existence of triple or even quadruple black hole systems. If 3 black holes interact gravitationally, the dynamics become chaotic and unpredictable. 2 might merge while the third is ejected at high speed, kicked out of the system entirely, or all 3 might dance around each other for millions of years before eventually merging in some combination. A few gravitational wave signals have shown hints of complexity that might indicate more than 2 black holes were involved. But confirming such systems will require more data and better models. Binary black holes also offer a unique way to test general relativity in its most extreme regime. When two black holes merge, spacetime is warped so violently that nonlinear effects dominate. Einstein's equations predict specific patterns in the gravitational waves emitted during the inspiral, merger, and ring-down phases. So far, every observed merger has matched these predictions with remarkable precision, confirming that general relativity holds even under the most extreme conditions. Any deviation from the predicted waveforms could signal new physics, such as modifications to gravity at strong field or corrections from quantum mechanics. Looking forward, the next generation of gravitational wave detectors will revolutionize the field. The planned Laser Interferometer Space Antenna, or LISA, will be a space-based detector sensitive to much lower frequency gravitational waves. This will allow it to detect mergers of supermassive black holes, events that occur when entire galaxies collide and their central black holes eventually merge. LISA will also be able to track binary black holes years before they merge, providing early warnings that could allow telescopes to search for electromagnetic counterparts. Ground-based detectors are also being upgraded with increased sensitivity that will allow them to detect black hole mergers out to greater distances and with higher precision. Binary black holes are more than just curiosities. They are cosmic laboratories where gravity is pushed to its limits, where space-time is torn and reshaped, and where we can test our deepest theories of the universe. Every detection adds to our understanding of how black holes form, evolve, and interact. And with each new merger, we hear the universe speaking in a language we have only just learned to understand: the language of gravitational waves. Rogue black holes. Most black holes stay where they are born, anchored by gravity to star clusters, galaxies, or companion stars. But not all black holes follow the rules. Some are ejected from their birthplaces, flung into the depths of space by violent kicks or gravitational slingshots. These are rogue black holes, cosmic wanderers drifting through the void with no home, no companion, and no visible sign of their presence. They are invisible predators, detectable only through their gravitational influence, and they represent one of the most difficult types of black holes to find. Rogue black holes can form in several ways. The most common is through a supernova kick. When a massive star collapses, the explosion is not always symmetric. If the core collapses asymmetrically, or if the neutrinos emitted during the collapse are unevenly distributed, the resulting black hole can receive a kick, a sudden jolt that sends it flying through space at hundreds of kilometers per second. Most of the time, this kick is small enough that the black hole remains bound to its host star cluster or galaxy. But occasionally, the kick is strong enough to exceed the escape velocity, and the black hole is ejected entirely. It then becomes a rogue, wandering through the galaxy with no gravitational anchor. Another way rogue black holes can form is through gravitational interactions in dense star clusters. In regions where thousands of black holes and stars are packed closely together, gravitational encounters are common. Two black holes might merge, and the resulting black hole could receive a recoil kick from the gravitational waves emitted during the merger. This recoil can be strong enough to eject the black hole from the cluster, sending it on a solitary journey through space. Similarly, in a three-body interaction, one object might be ejected at high speed while the other two remain bound. If the ejected object is a black hole, it becomes a rogue. Supermassive black holes can also become rogues. When two galaxies merge, their central black holes sink toward the center of the newly formed galaxy and begin to orbit each other. If a third black hole is present, the dynamics become chaotic. One black hole might be ejected at speeds of thousands of kilometers per second, enough to escape the galaxy entirely. Even without a third black hole, the merger of two supermassive black holes releases gravitational waves asymmetrically, and the recoil can kick the combined black hole out of the galactic center. While such events are rare, simulations suggest they should happen occasionally, and a few candidate wandering supermassive black holes have been identified in surveys. Finding rogue black holes is extraordinarily difficult. They emit no light and rarely encounter other objects, so they remain invisible. The best chance of detecting them is through gravitational microlensing, a phenomenon where the black hole's gravity bends and magnifies light from a background star. As the black hole passes in front of the star appears to brighten temporarily. By measuring the duration and shape of this brightening, astronomers can infer the mass and speed of the lensing object. If the mass is too high to be a star, and the object shows no other signs of light, it is likely a black hole. Several microlensing surveys are currently underway, and a handful of candidates have been identified, though confirming them as black holes requires careful analysis. One of the most intriguing rogue black hole candidates was discovered in 2022. Astronomers observed a star that brightened over several months in a way consistent with gravitational lensing by a massive, dark object. The lensing event lasted long enough to suggest the object was moving relatively slowly and was quite massive, possibly a black hole weighing several solar masses. If confirmed, it would be one of the first isolated stellar mass black holes ever directly detected. The discovery highlights the potential of microlensing as a tool for finding these otherwise invisible objects. Rogue black holes could be far more common than we realize. Estimates suggest that there could be hundreds of millions of stellar mass rogue black holes wandering through the Milky Way alone. Most were likely ejected from their birthplaces billions of years ago and have been drifting ever since. Some pass through the galactic disk, others roam the halo, the diffuse region surrounding the galaxy. Occasionally, one might pass through our solar system, but there is no cause for alarm. Space is vast, and the chances of a rogue black hole coming anywhere near Earth are vanishingly small. Even if one did pass nearby, its gravitational influence would be localized, affecting only objects that came very close. Rogue black holes also raise interesting questions about the history of star formation and galactic evolution. Every rogue was once part of a binary system or a star cluster. By studying the population of rogues, we can learn about the dynamics of these environments, the frequency of supernovae, and the conditions under which black holes receive strong kicks. Rogue supermassive black holes, if they exist, could tell us about the rate of galaxy mergers and the prevalence of triple black hole systems in the early universe. The existence of rogue black holes reminds us that the universe is not static. Objects do not always stay where they form. Stars are ejected from clusters, planets are thrown out of solar systems, and black holes wander through the cosmos. In this way, rogues are a natural consequence of the chaotic dynamic nature of gravity. They are the outliers, the runaways, the black holes that escaped. And while they are difficult to find, each one discovered adds a new chapter to the story of how black holes move through and shape the universe. Quasars and active galactic nuclei. Some black holes do more than simply exist. They roar. They blaze across the universe with such ferocity that they can be seen from billions of light years away. These are the black holes at the centers of quasars and active galactic nuclei, feeding machines that convert matter into energy with terrifying efficiency. They are among the most luminous objects in the cosmos, and they reveal black holes not as passive voids but as engines of creation and destruction on a galactic scale. A quasar, short for quasi-stellar radio source, looks like a bright point of light, similar to a star, but it is anything but. Quasars are the brilliant cores of distant galaxies, powered by supermassive black holes, consuming enormous amounts of material. When gas and dust fall toward a supermassive black hole, they do not plunge directly in. Instead, they spiral inward, forming an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow across the electromagnetic spectrum. The energy released is so immense that a single quasar can outshine its entire host galaxy, which may contain hundreds of billions of stars. From our perspective on Earth, we see only the brilliant core, a beacon shining across the universe. The first quasars were discovered in the 1960s, when astronomers noticed strange radio sources that appeared star-like in optical images. When they measured the spectra of these objects, they found something shocking. The light was enormously redshifted, indicating the objects were billions of light years away. Yet they were still bright enough to see from Earth, which meant they had to be emitting staggering amounts of energy. At first, no one could explain what could produce such luminosity. Some proposed exotic physics, even white holes or matter-antimatter annihilation. But the answer turned out to be simpler and more profound: supermassive black holes. The physics of quasars is governed by accretion. As matter falls toward the black hole, gravitational potential energy is converted into kinetic energy and then into heat through friction and compression. The efficiency of this process is remarkable. In nuclear fusion, which powers stars, only about 0.7% of the mass is converted into energy. In accretion onto a black hole, the efficiency can reach 10% or more, making it one of the most efficient energy conversion processes in the universe. A supermassive black hole consuming just a few solar masses of material per year can produce the luminosity of trillions of suns. Quasars were most common in the early universe, when galaxies were young and gas was abundant. Between 1 and 3 billion years after the Big Bang, quasars were everywhere, their light now stretched into the infrared by cosmic expansion. As the universe aged and galaxies exhausted their gas supplies, quasars became rarer. Today, most supermassive black holes are quiet, fed only by occasional infalling stars or wisps of gas. But in the past, they were voracious, shaping the galaxies around them through the sheer power of their radiation and outflows. Not all active black holes are quasars. The broader category is called active galactic nuclei, or AGN. This includes quasars, but also dimmer versions like Seyfert galaxies and radio galaxies. The differences often come down to the orientation of the accretion disk relative to our line of sight and the rate at which the black hole is feeding. If we view the disk edge on, we see the full brilliance of the accretion disk. If we view it face on, or if the black hole is feeding more slowly, the emission is weaker. Some AGN also produce powerful jets, narrow beams of particles and radiation shot out along the black hole's rotation axis at nearly the speed of light. These jets can extend for hundreds of thousands of light years, dwarfing the host galaxy itself. The mechanism behind these jets is still not fully understood, but it likely involves magnetic fields, twisted and amplified by the spinning accretion disk and black hole. As gas spirals inward, it drags magnetic field lines with it, wrapping them tighter and tighter. Eventually, the magnetic pressure becomes so strong that it launches material outward along the rotation axis, creating twin jets shooting in opposite directions. The particles in these jets, mostly electrons and protons, are accelerated to extreme energies, producing radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. One of the most famous examples is the galaxy M87, the same galaxy whose supermassive black hole was imaged by the Event Horizon Telescope. M87's black hole drives a jet that extends for about 5,000 light-years, glowing brightly in radio and X-ray wavelengths. The jet is so energetic that it punches through the surrounding gas, creating shocks and heating the intergalactic medium. This energy injection prevents gas from cooling and collapsing to form new stars, regulating the growth of the galaxy. In this way, AGN act as thermostats, controlling star formation and shaping galaxy evolution. Quasars and AGN also serve as cosmic lighthouses, illuminating the distant universe and allowing us to study conditions in the early cosmos. Because they are so bright, we can detect them even when the universe was very young. By studying their spectra, we can learn about the composition of the intergalactic medium, the rate of cosmic expansion, and the growth of structure over time. Quasars have been used to map the large-scale structure of the universe, trace the distribution of dark matter, and measure the expansion history of the cosmos. But quasars are not eternal. Eventually, the supply of gas runs out, and the accretion rate drops. The quasar dims, fading into obscurity. The supermassive black hole remains, but it becomes dormant, lurking quietly at the galactic center until a new influx of gas reawakens it. This cycle of activity and quiescence has repeated throughout cosmic history, with each galaxy experiencing brief episodes of intense activity separated by long periods of calm. Our own Milky Way likely hosted a quasar phase in its distant past, though today Sagittarius, a star, is nearly silent. The study of quasars and AGN has revolutionized our understanding of black holes, galaxies, and the universe itself. They reveal that black holes are not just endpoints of stellar evolution, but active participants in cosmic evolution. They shape galaxies, drive winds and jets, regulate star formation, and enrich the intergalactic medium with energy and metals. They are the most powerful sustained sources of energy in the universe, and they remind us that black holes are not merely objects of darkness, but also sources of light. Reissner-Nordstrom black holes. So far, we have discussed black holes defined by mass and spin, but general relativity allows for one more property, electric charge. A black hole with electric charge is called a Reissner-Nordstrom black hole, and it represents one of the most exotic and theoretically intriguing types of black holes. In practice, such black holes are almost certainly absent from the real universe. But studying them reveals deep insights into the nature of spacetime, event horizons, and the limits of physical theory. The concept is straightforward. Imagine taking a Schwarzschild black hole and adding electric charge. Just as the black hole curves spacetime through its mass, it also creates an electric field that extends outward to infinity. The presence of this charge modifies the structure of spacetime around the black hole, altering the shape and properties of the event horizon. In fact, a Reissner-Nordstrom black hole has two horizons, an outer event horizon and an inner Cauchy horizon. Between these two surfaces, spacetime has unusual properties, and the geometry becomes even more exotic than in a Schwarzschild black hole. The outer horizon functions much like the event horizon of a Schwarzschild black hole. Once you cross it, you cannot escape. But unlike a Schwarzschild black hole, you do not immediately plunge toward a singularity. Instead, you pass through a region of space between the two horizons, where spacetime remains traversable. Eventually, you reach the inner Cauchy horizon, and beyond that lies the singularity. But the singularity in a Reissner-Nordstrom black hole is not a point. It is a time-like surface, meaning that unlike the space-like singularity of a Schwarzschild black hole, you could theoretically avoid hitting it by choosing the right trajectory. Some solutions to Einstein's equations even suggest that passing through the inner horizon could lead to other regions of space-time, though most physicists believe these solutions are unphysical and would be destroyed by quantum effects. Why are Reissner-Nordstrom black holes so rare in nature? The reason is simple. Opposite charges attract. If a black hole had a net positive charge, it would quickly attract negatively charged particles from the surrounding environment, neutralizing the charge. Similarly, a negatively charged black hole would attract positive particles. The timescale for neutralization is extremely short, often less than seconds. Any astrophysical black hole that formed with charge would lose it almost immediately. For this reason, astronomers do not expect to find charged black holes in the wild. They are theoretical constructs, useful for exploring the mathematics of general relativity but not for describing real objects. Despite their impracticality, Reissner-Nordstrom black holes are valuable for thought experiments. They highlight the role of charge in general relativity and demonstrate that event horizons are not always single surfaces. They also illustrate the concept of extremal black holes. If you increase the charge of a Reissner-Nordstrom black hole, the two horizons move closer together. At a certain critical value, they merge into a single horizon. This is called an extremal Reissner-Nordstrom black hole, and it represents the maximum charge a black hole of a given mass can have. If you tried to add more charge, the horizons would disappear entirely, exposing the singularity to the outside universe and creating a naked singularity. Most physicists believe this is forbidden by the cosmic censorship conjecture, which states that singularities must always be hidden behind event horizons. Reissner-Nordstrom. Black holes also play a role in certain speculative theories. In string theory and other approaches to quantum gravity, particles like electrons are sometimes modeled as extremal Reissner-Nordstrom black holes. The idea is that at the smallest scales, particles might not be point-like, but rather tiny black holes with charge and mass. While this is far from proven, it illustrates how studying exotic black hole solutions can inform our understanding of fundamental physics. Another interesting feature of charged black holes is their interaction with electromagnetic fields. A charged black hole creates a radial electric field, and if it is immersed in an external magnetic field, the interplay between gravity and electromagnetism produces complex dynamics. This has implications for understanding how charged particles behave near black holes and how energy can be extracted from rotating charged black holes through electromagnetic processes. In the end, Reissner-Nordstrom black holes are primarily mathematical curiosities. They are solutions to Einstein's equations that demonstrate the richness and complexity of general relativity. They teach us about the interplay between charge, mass, and spacetime curvature. And while we do not expect to find them in nature, their study deepens our understanding of what black holes are and what they could be. They remind us that the universe of possibilities described by general relativity is far larger than the universe we actually inhabit. Kerr-Newman black holes. If we combine the rotation of a Kerr black hole with the electric charge of a Reissner-Nordstrom black hole, we arrive at the most general black hole solution in classical general relativity, the Kerr-Newman black hole. This is a black hole with mass, spin, and electric charge, the full set of properties allowed by Einstein's equations. It represents the complete picture, the ultimate expression of what a black hole can be according to our current understanding of gravity. And yet, like its charged cousin, the Kerr-Newman black hole is almost certainly absent from the real universe, existing primarily as a mathematical playground for physicists exploring the limits of theory. The Kerr-Newman solution was discovered in 1965 by Ezra Newman and colleagues, building on Roy Kerr's earlier work on rotating black holes. The mathematics is formidable, involving complex geometries where spacetime is warped by mass, twisted by rotation, and threaded by electric fields. The result is a black hole with an oblate event horizon, an ergosphere where spacetime is dragged into rotation, and an electric field extending outward to infinity. Like the Reissner-Nordstrom black hole, it has two horizons, an outer event horizon and an inner Cauchy horizon. Between them lies a region where the geometry is even more exotic than in simpler black holes. The presence of both spin and charge creates unusual effects. The rotation drags spacetime around the black hole, while the charge creates a radial electric field. Together, these effects modify the structure of the ergosphere and the properties of particle orbits near the black hole. Charged particles experience both gravitational and electromagnetic forces, leading to complex trajectories that differ significantly from those around uncharged black holes. In principle, the interplay between rotation and charge could be used to extract even more energy from the black hole than the Penrose process allows, through electromagnetic interactions with the spinning spacetime. But as with Reissner-Nordstrom black holes, the charge makes Kerr-Newman black holes unrealistic in astrophysical settings. Any black hole that formed with a net charge would quickly attract oppositely charged particles from the surrounding plasma, neutralizing itself in seconds or less. The universe is filled with charged particles, from electrons to protons to ions of various elements, and these particles would swarm any charged black hole, eliminating its charge through accretion. For this reason, astronomers do not search for Kerr-Newman black holes in nature. They are curiosities, solutions to equations that demonstrate the mathematical richness of general relativity, but do not correspond to observable objects. Nevertheless, Kerr-Newman black holes serve important theoretical purposes. They complete the classification of black hole solutions in classical general relativity. According to the no-hair theorem, a black hole in equilibrium can be completely described by just three properties: mass, angular momentum, and electric charge. Any other information about the matter that formed the black hole is lost, erased by the collapse. The Kerr-Newman solution proves this theorem explicitly by showing that these three parameters are sufficient to specify the entire spacetime geometry around the black hole. Everything else, the composition of the original star, its magnetic field, its temperature, is gone, hidden behind the event horizon or radiated away. Kerr-Newman. Black holes also appear in certain speculative contexts. Some models of elementary particles, particularly in string theory, describe electrons and other charged particles as tiny extremal Kerr-Newman black holes. In these models, the particle's mass corresponds to the black hole's mass, its charge to the electric charge, and its spin to the angular momentum. While this is far from a proven description of reality, it illustrates how black hole physics can intersect with particle physics at the most fundamental level. If particles are indeed microscopic black holes, then the Kerr-Newman solution describes not just exotic astrophysical objects, but the basic building blocks of matter itself. Another area where Kerr-Newman black holes prove useful is in studying the mathematical structure of spacetime. The solutions exhibit features like closed time-like curves, regions where the geometry allows paths that loop back in time. Most physicists believe these features are unphysical, artifacts of the classical theory that would be eliminated by quantum effects. But studying them helps us understand the limits of general relativity and the conditions under which the theory breaks down. They highlight the need for a quantum theory of gravity that can handle the extreme conditions near singularities and inside event horizons. The existence of multiple horizons in Kerr-Newman black holes also raises fascinating questions about what lies beyond the inner horizon. In principle, the spacetime geometry extends past the Cauchy horizon into other regions, possibly even other universes. Some solutions suggest the presence of wormholes connecting different parts of spacetime, or white holes expelling matter into new regions. These possibilities are tantalizing, but almost certainly unrealistic. Perturbations from the outside universe, quantum fluctuations, and instabilities near the Cauchy horizon would likely destroy these exotic structures, replacing them with a singularity or some other quantum gravitational object we do not yet understand. In practice, Kerr-Newman black holes are mathematical constructs, the final entry in the catalogue of black hole solutions. They represent the endpoint of a logical progression. Start with mass alone to get Schwarzschild, add rotation to get Kerr, add charge to get Reissner-Nordstrom, and combine both to get Kerr-Newman. This progression demonstrates the elegance of general relativity, how a single theory can encompass such a wide variety of phenomena. And while we may never find a Kerr-Newman black hole in nature, the solution itself is a testament to the power of mathematical physics to explore possibilities beyond the observable universe. Hawking radiation and evaporating black holes. Black holes are often described as cosmic prisons from which nothing can escape. But in 1974, Stephen Hawking discovered that this picture is incomplete. Black holes, he realized, are not entirely black. They emit radiation, slowly losing mass over time through a quantum mechanical process that occurs near the event horizon. This phenomenon, now known as Hawking radiation, fundamentally changed our understanding of black holes and raised profound questions about the nature of information, entropy, and the ultimate fate of the universe. The key to Hawking radiation lies in quantum mechanics. According to quantum field theory, empty space is not truly empty. It seethes with virtual particles. Pairs of particles and antiparticles that pop into existence exist for a fleeting instant and then annihilate each other, disappearing back into the vacuum. This process happens everywhere in the universe, constantly, but it usually has no observable effect because the particle pairs exist for such a short time. Near a black hole's event horizon, however, something remarkable can happen. If a particle-antiparticle pair forms just outside the horizon, one particle might fall into the black hole while the other escapes to infinity. To an outside observer, it appears as though the black hole has emitted a particle. But where does the energy for this particle come from? It comes from the black hole itself. When one particle falls in, it carries negative energy relative to the outside universe, causing the black hole to lose mass. The escaping particle, meanwhile, carries positive energy, which we observe as radiation. This process is incredibly slow for large black holes, but it accelerates as the black hole shrinks. The smaller the black hole, the hotter the radiation, and the faster the evaporation. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A black hole with the mass of the Sun has a temperature of only about 60 billionths of a Kelvin, far colder than the cosmic microwave background. Such a black hole would actually absorb more energy from the universe than it radiates, growing rather than shrinking. But a black hole with the mass of a mountain would have a temperature of billions of Kelvin, glowing white hot and evaporating rapidly. The implications are staggering. Hawking radiation means that black holes are not eternal. Given enough time, they will evaporate completely, shrinking until they vanish in a final burst of energy. For stellar mass black holes, this process takes an incomprehensibly long time, on the order of 10 to the 67 years or more. For supermassive black holes, the timescale is even longer, extending to 10 to the 100 years, far beyond the current age of the universe. But for small black holes, particularly quantum or primordial black holes, evaporation can happen quickly. A black hole with the mass of an asteroid would evaporate in less than the age of the universe. A black hole with the mass of a mountain would vanish in a second. Hawking radiation also introduces a deep puzzle known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. If you throw a book into a fire, the information in the book is not lost. It is scrambled into the smoke, ash, and radiation, but in principle, it could be reconstructed. But what happens if you throw the book into a black hole? Hawking radiation is thermal, meaning it carries no information about what fell into the black hole. It is random, characterized only by temperature, with no distinguishing features. If the black hole evaporates completely, releasing only featureless thermal radiation, then the information in the book appears to have been destroyed, violating the principles of quantum mechanics. This paradox has occupied physicists for decades. Several solutions have been proposed. One idea is that information is encoded on the event horizon itself, in subtle correlations that we have not yet learned to detect. Another is that information escapes through non-thermal corrections to Hawking radiation, tiny deviations from perfect randomness that carry information about the black hole's contents. A third possibility is that black holes do not evaporate completely, but leave behind remnants, tiny stable objects that preserve all the information. Yet another idea involves holography, the notion that all the information about a black hole's interior is encoded on its two-dimensional surface, much like a hologram encodes three-dimensional information. Recent developments have pointed toward a resolution involving quantum entanglement and the structure of spacetime itself. Some researchers believe that information is not lost, but rather scrambled in a highly complex way and gradually released as the black hole evaporates. The process would be so intricate that it appears random to any observer who does not have access to the complete quantum state of the entire system. Others suggest that the paradox reveals a fundamental tension between quantum mechanics and general relativity, a tension that can only be resolved by a complete theory of quantum gravity. Hawking radiation also has implications for the ultimate fate of the universe. In the far future, long after all stars have burned out and all ordinary matter has decayed, black holes will be the last massive objects remaining. They will sit in the darkness, slowly radiating away their mass. Eventually, even the largest supermassive black holes will evaporate, and the universe will be left with nothing but a thin soup of particles and radiation, spread ever more thinly as space continues to expand. This era, called the black hole era, will last from about 10 to the 40 years to 10 to the 100 years after the Big Bang. After that, only the photon era remains, a universe of cold, dilute radiation stretching toward infinite time. The discovery of Hawking radiation transformed black holes from purely classical objects into quantum entities. It revealed that black holes have entropy, a measure of disorder, and temperature, properties we normally associate with thermodynamics. This connection between gravity, quantum mechanics, and thermodynamics has led to deep insights into the nature of space-time, suggesting that gravity itself may be an emergent phenomenon arising from the statistical behavior of underlying quantum degrees of freedom. Black holes, in this view, are not just objects in space-time, but windows into the fundamental structure of reality. Detecting Hawking radiation from astrophysical black holes is virtually impossible with current technology. The radiation is far too weak, drowned out by other sources of light and energy. But scientists have created analog systems in laboratories, using sound waves in fluids or light in optical materials to simulate black hole physics. These analogs have successfully demonstrated radiation, similar to Hawking radiation, providing indirect evidence that the phenomenon is real. And while we may never directly observe Hawking radiation from a real black hole, the theoretical implications continue to shape our understanding of physics at the deepest level. White holes. If black holes are regions of space-time where nothing can escape, what about the opposite? Could there exist regions where nothing can enter, where matter and energy are only expelled? This is the concept of a white hole, a hypothetical object that is the time reverse of a black hole. White holes appear as solutions to Einstein's equations, but whether they can exist in nature remains one of the most speculative questions in physics. The mathematics of white holes is straightforward. Take the Schwarzschild solution for a black hole and reverse the direction of time. The result is a white hole, an object with an event horizon that works in reverse. Instead of a boundary beyond which nothing can escape, it is a boundary beyond which nothing can enter. Matter and light can exit the white hole, streaming outward into the universe, but nothing can fall in. If you tried to approach a white hole, you would find yourself unable to reach the horizon. The closer you got, the more strongly you would be repelled, not by any force, but by the geometry of space-time itself. White holes have the same mass as black holes and create the same gravitational field outside their event horizons. From a distance, a white hole would look identical to a black hole, an invisible object detectable only through its gravitational influence. But up close, the difference would be stark. While a black hole pulls everything in, a white hole pushes everything out. The horizon is a one-way membrane, but in the opposite direction. Despite their mathematical elegance, white holes face severe problems. The most obvious is stability. Black holes are stable because they are endpoints, sinks where matter accumulates. White holes, as sources, are inherently unstable. Any small perturbation, any infalling particle or gravitational wave would disrupt the delicate structure. Since white holes expel matter but cannot absorb it, there is no mechanism to dissipate disturbances. Most physicists believe that even if a white hole could form, it would immediately collapse or transform into something else, possibly a black hole. Another issue is causality. White holes, by their nature, require a preferred moment in time when they begin to expel matter. But where does this matter come from? In the time-reversed picture, it emerges from the singularity at the center. But this raises the question of what determines when and how the matter is expelled. Unlike black holes, which form from collapsing matter in a well-understood process, white holes would require initial conditions that seem contrived and unphysical. There is no known mechanism in nature that would create a white hole. Some physicists have speculated that white holes could be connected to black holes through wormholes, hypothetical tunnels through space-time. In this picture, matter falling into a black hole could travel through the wormhole and emerge from a white hole in another region of space-time, possibly even another universe. This idea has captured the imagination of science fiction writers and the public, but it faces insurmountable problems. Wormholes, even if they could exist, would be unstable, collapsing before anything could pass through. And the passage through a black hole's singularity would likely destroy any object, leaving nothing to emerge from the white hole. Another intriguing possibility is that white holes are related to the Big Bang itself. Some cosmologists have proposed that the Big Bang, the moment when the universe began, could be understood as a white hole, an event horizon in time beyond which nothing existed. In this view, the universe emerged from a singularity, expelling matter and energy in all directions, much like a white hole. This is a provocative idea, but it remains speculative and lacks a solid theoretical foundation. In recent years, some researchers have suggested that the final stages of black hole evaporation might produce white hole-like behavior. As a black hole evaporates through Hawking radiation, it shrinks and heats up. In the final moments, quantum effects become dominant, and the black hole might undergo a quantum transition, transforming into a white hole that explosively releases the remaining mass energy. This process, sometimes called a black hole to white hole transition, could explain what happens at the endpoint of black hole evaporation and might even resolve the information paradox. However, these ideas are highly speculative and await confirmation from a complete theory of quantum gravity. White holes also appear in certain exotic cosmological models. In loop quantum gravity, one approach to quantum gravity, the singularity at the center of a black hole is replaced by a quantum bounce, a region where space-time undergoes a transition. Some solutions suggest that this bounce could connect a black hole to a white hole, with the black hole in our universe feeding matter into a white hole in another region of space-time. These models are mathematically consistent but remain far from observational confirmation. For now, white holes remain entirely theoretical. No white hole has ever been observed, and most physicists doubt they exist in nature. They are solutions to equations that illustrate the richness of general relativity but do not correspond to real objects. Still, they serve a purpose. They remind us that the laws of physics are often time-symmetric, that for every process going forward in time, there is a corresponding process going backward. And they challenge us to think deeply about why the universe we observe is so asymmetric in time. Why black holes are common, but white holes are absent. White holes are the ghosts of general relativity, phantoms that exist in mathematics but not in reality. They are the cosmic opposites of black holes, the objects that could exist but probably do not. And in their impossibility, they teach us something profound about the nature of time, entropy, and the arrow of causality that points from past to future. Wormholes and traversable black holes. Among the most tantalizing predictions of general relativity are wormholes, hypothetical tunnels through space-time that connect distant regions of the universe or even separate universes entirely. Unlike black holes and white holes, which are one-way barriers, wormholes would allow travel in both directions, providing shortcuts through the cosmos. They are the stuff of science fiction, but they are also legitimate solutions to Einstein's equations. Objects that could, in principle, exist. The question is whether nature actually produces them, and if so, whether they could ever be used for travel. The simplest wormhole is the Einstein-Rosen bridge, a solution discovered in 1935 by Albert Einstein and Nathan Rosen. This structure connects two black holes through a tunnel in space-time. Imagine two Schwarzschild black holes, one in our universe, and one in a distant region or another universe entirely. The Einstein-Rosen bridge links their event horizons, creating a passage between them. In theory, you could enter one black hole and exit through the other, but there is a fatal flaw. The bridge is not traversable. The tunnel collapses faster than light can cross it, crushing anything that tries to pass through. By the time you entered one end, the tunnel would have already pinched off, and you would be trapped inside, doomed to hit the singularity. To make a wormhole traversable, you need something exotic, negative energy. In general relativity, matter and energy normally have positive density, creating attractive gravity, but negative energy would have repulsive effects, pushing space-time outward instead of pulling it inward. If you could line the throat of a wormhole with negative energy, you could hold it open, preventing it from collapsing. The wormhole would then be stable, and travelers could pass through safely, emerging light years away in a fraction of the time it would take to traverse the distance normally. Negative energy sounds like science fiction, but it is not entirely impossible. Quantum mechanics allows for negative energy densities under certain conditions, a phenomenon related to the Casimir effect. When two parallel metal plates are placed very close together in a vacuum, the space between them has slightly less energy than the surrounding vacuum, creating a region of negative energy density. This effect has been measured in laboratories, confirming that negative energy is real. However, the amount of negative energy produced by the Casimir effect is incredibly small, far too small to stabilize a wormhole large enough for anything to pass through. Even if we could gather enough negative energy, other problems remain. A traversable wormhole would require careful engineering to avoid instabilities. Any disturbance, such as a pulse of light or a particle passing through, could cause the wormhole to collapse. Maintaining stability would require active feedback systems, constantly adjusting the distribution of negative energy to counteract perturbations. This is far beyond anything we can currently imagine building, even in principle. Another challenge is that wormholes, if they could be stabilized, might enable time travel. If you could move one mouth of a wormhole at high speed, or place it in a strong gravitational field, time dilation would cause the two mouths to experience time differently. You could then enter one mouth and emerge from the other at an earlier time, creating a closed, time-like curve. This raises all the familiar paradoxes of time travel. If you go back and prevent your own birth, do you still exist? Most physicists believe that the laws of physics conspire to prevent such paradoxes, perhaps through quantum effects that destabilize any wormhole that threatens causality. Despite these obstacles, wormholes continue to fascinate physicists. They are not just curiosities, but probes into the nature of space-time. Studying wormholes helps us understand the limits of general relativity, the role of quantum mechanics in gravity, and the structure of the vacuum itself. Some theories of quantum gravity, such as string theory, predict that space-time at the smallest scales is filled with tiny wormholes, constantly forming and disappearing. These quantum wormholes, far too small for anything to traverse, might contribute to the properties of empty space, affecting the vacuum energy and the behavior of particles. There is also speculation that black holes and wormholes could be connected through quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical idea: that entangled particles are connected by tiny wormholes, a concept known as ER equals EPR. In this view, quantum entanglement, the mysterious connection between particles that seems to allow instant communication, is actually a manifestation of wormholes in space-time. If true, this would unify two of the deepest mysteries in physics, revealing that wormholes are not just exotic objects, but fundamental features of reality. For now, wormholes remain entirely theoretical. No wormhole has ever been observed, and no mechanism for creating one is known. They are solutions to equations, possibilities allowed by the mathematics of general relativity, but not yet found in nature. Whether they exist, whether they can be stabilized, and whether they could ever be used for travel are questions that await answers from future theories and experiments. But even as hypothetical objects, wormholes push the boundaries of what we think is possible, challenging us to imagine a universe far stranger and more connected than we ever dreamed. Naked singularities. A singularity is a point where space-time curvature becomes infinite, where the laws of physics break down. In every black hole we have discussed so far, the singularity is hidden behind an event horizon, shielded from view. This is not an accident. Most physicists believe in a principle called cosmic censorship, which states that nature always hides singularities behind horizons. A naked singularity, a singularity without an event horizon, would violate this principle, exposing the breakdown of physics to the outside universe. The question is, can naked singularities exist? And if so, what would they imply? The cosmic censorship conjecture was proposed by Roger Penrose in 1969. It comes in two versions, weak and strong. Weak cosmic censorship states that singularities cannot be visible from infinity, meaning they must be enclosed by event horizons. Strong cosmic censorship goes further, stating that the laws of physics remain predictive everywhere outside the horizon with no pathological features. Both conjectures are motivated by the desire to preserve predictability and causality in physics. If naked singularities exist, we lose the ability to predict the future, because anything could emerge from the singularity without warning. Several scenarios could, in principle, produce naked singularities. One involves overspinning a black hole. A Kerr black hole has a maximum rotation rate. If you tried to spin it faster by adding angular momentum, the event horizon would shrink. At a critical spin, the horizon would disappear entirely, leaving the ring singularity exposed. This is called an over-extremal Kerr black hole, and it would be a naked singularity. However, most attempts to overspin a black hole through realistic processes fail. When you try to add angular momentum by dropping in spinning matter, the black hole's horizon grows just fast enough to keep the singularity hidden. Another possibility involves the collapse of highly asymmetric matter distributions. In the 1990s, physicists ran computer simulations of collapsing clouds with specific shapes and found that in some cases, the collapse produced naked singularities. These configurations are highly contrived, requiring precise initial conditions that are unlikely to occur in nature. But they show that general relativity, on its own, does not strictly forbid naked singularities. The question is whether additional physics, such as quantum mechanics, steps in to prevent them. If naked singularities exist, they would have bizarre properties. Near a singularity, space-time curvature is infinite, and tidal forces would be infinitely strong. Anything approaching would be torn apart, stretched and compressed without limit. But unlike a black hole, where this happens behind a horizon, a naked singularity would be visible from the outside. You could, in principle, observe the singularity directly, seeing light rays emerge from the region where physics breaks down. What you would actually see is unclear. The singularity might appear as a point of infinitely bright light, or it might be obscured by extreme lensing effects that distort the surrounding space. Naked singularities would also allow violations of causality. Near a singularity, the structure of spacetime becomes so warped that time-like and space-like directions can swap, creating closed, time-like curves. You could, in theory, travel in a loop through time, visiting your own past. This leads to all the familiar time travel paradoxes, such as the grandfather paradox. Most physicists find this deeply troubling and take it as evidence that naked singularities cannot exist in the real universe. Some researchers have argued that quantum mechanics might save cosmic censorship. At the Planck scale, quantum effects become important, and they might smooth out the singularity or replace it with a different structure. In loop quantum gravity, for instance, singularities are replaced by quantum bounces, regions where space-time undergoes a transition but remains finite. If this is correct, then even if classical general relativity predicts naked singularities, quantum gravity would eliminate them, preserving cosmic censorship at a deeper level. There is also the possibility that cosmic censorship is simply wrong. Perhaps nature does allow naked singularities, and we have just not observed one yet. Some astrophysicists have searched for observational signatures, such as unusual gravitational lensing or exotic radiation patterns that might indicate the presence of a naked singularity. So far, no candidates have been found, but the search continues. If a naked singularity were ever discovered, it would force a revolution in our understanding of spacetime, causality, and the limits of physical law. For now, cosmic censorship remains a conjecture, widely believed but not proven. Naked singularities exist as solutions to Einstein's equations, but whether they correspond to real objects is unknown. They are the forbidden fruit of general relativity, objects that could exist but probably should not, anomalies that would break the predictability of physics. And in their impossibility, or their possibility, they challenge us to understand what the universe truly allows. Gravitational wave astronomy and black hole mergers. For most of human history, we studied the universe through light. Telescopes collected photons, and from those photons, we learned about stars, galaxies, and the structure of the cosmos. But light has limitations. It is absorbed by dust, scattered by gas, and emitted only by objects that are hot or energized. Black holes, by definition, do not emit light, making them invisible. But in 2015, a new window onto the universe opened. For the first time, we detected gravitational waves, ripples in spacetime itself produced by colliding black holes. This marked the beginning of gravitational wave astronomy, a revolutionary field that allows us to observe the universe in an entirely new way. Gravitational waves are distortions in spacetime that propagate outward at the speed of light. They are produced whenever massive objects accelerate, but the effect is usually so weak that it is undetectable. Only the most violent events in the universe, such as the collision of black holes or neutron stars, produce gravitational waves strong enough to measure. These waves stretch and compress space as they pass, alternately lengthening and shortening distances by tiny amounts. The effect is extraordinarily small. When the first gravitational wave reached Earth in 2015, it changed the distance between the two ends of the LIGO detector by less than 1/1000th the diameter of a proton. Detecting such a minute distortion requires exquisite precision. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses two enormous L-shaped detectors, each with arms 4 kilometers long. Laser beams travel down the arms, bounce off mirrors, and return to a central station where they interfere. If a gravitational wave passes through, it stretches one arm and compresses the other, causing a tiny shift in the interference pattern. By monitoring this pattern, scientists can detect the passage of gravitational waves and decode the information they carry. The first detection, known as GW150914, came from two black holes weighing 36 and 29 solar masses. They had been orbiting each other for billions of years, slowly spiraling inward as they lost energy to gravitational waves. In the final seconds, their orbital speed increased dramatically, and they began circling each other hundreds of times per second. The gravitational waves they emitted grew stronger and stronger, rising in frequency like a chirp. When the black holes finally merged, they formed a single black hole weighing 62 solar masses. The missing 3 solar masses, about the mass of our Sun, were converted entirely into gravitational wave energy and radiated outward across the universe. The signal lasted only a fraction of a second, but it carried a wealth of information. By analyzing the waveform, scientists determined the masses of the two black holes, their spins, the distance to the system, and the properties of the final black hole. The detection confirmed that binary black holes exist, that they merge, and that gravitational waves are real. It also validated Einstein's theory of general relativity in its most extreme regime, where spacetime is violently warped by colliding black holes. Since 2015, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events. Most come from merging black holes, but some involve neutron stars or mixed systems. Each detection adds to our understanding of how black holes form, how often they merge, and what environments they inhabit. The data have revealed surprises, such as black holes heavier than expected, and mergers with unusual spin configurations. These observations are painting a picture of black hole populations across the universe, showing that black holes are more diverse than we thought. Gravitational wave astronomy also allows us to study the universe at distances and times that light cannot reach. The early universe, for instance, was opaque to light for the first 380,000 years after the Big Bang, because the plasma was too hot and dense for photons to travel freely. But gravitational waves pass through matter almost without interaction, meaning they could carry information from the very first moments after the Big Bang. Future detectors, such as the planned Laser Interferometer Space Antenna, or LISA, will be sensitive to low-frequency gravitational waves produced by supermassive black hole mergers, and possibly even by cosmic events in the primordial universe. LISA will operate in space, free from the seismic noise and atmospheric disturbances that limit ground-based detectors. It will consist of 3 spacecraft flying in formation, separated by millions of kilometers, using laser beams to measure tiny changes in distance. LISA will detect gravitational waves from merging supermassive black holes, events that occur when galaxies collide. These mergers release far more energy than stellar mass black hole mergers, producing gravitational waves that can be detected across the entire observable universe. LISA will also be able to track binary black holes years before they merge, providing early warnings that could allow electromagnetic telescopes to observe the events in multiple wavelengths. Gravitational wave detectors on the ground are also being upgraded. The next generation of detectors, such as the Einstein telescope and Cosmic Explorer, will be even more sensitive, capable of detecting black hole mergers from the edge of the observable universe. They will see every stellar mass black hole merger that occurs within billions of light years, providing a complete census of black hole populations. These detectors will also be able to measure the properties of black holes with unprecedented precision, testing general relativity more rigorously, and searching for deviations that might hint at new physics. One of the most exciting prospects is the detection of gravitational waves from the early universe itself. In the first moments after the Big Bang, quantum fluctuations were amplified by cosmic inflation, creating ripples in spacetime that still propagate today as a background of gravitational waves. Detecting this primordial gravitational wave background would provide direct evidence of inflation and open a window onto the universe at energies far beyond anything we can achieve in particle accelerators. It would be the ultimate application of gravitational wave astronomy, using black holes and their collisions as tools to probe the birth of the cosmos. Gravitational wave astronomy has transformed our understanding of black holes. Before 2015, black holes were largely theoretical, objects we inferred from their effects on visible matter. Now we can hear them directly, listening to the sounds of space-time as black holes spiral, collide, and merge. We have entered an era where black holes are no longer hidden, but announced, their presence revealed by the very fabric of the universe they warp. And with each new detection, we learn more about these extraordinary objects and the cosmos they inhabit. The Event Horizon Telescope and black hole shadows. For decades, black holes were invisible, their existence inferred only from the motion of stars and gas. But in 2019, the world saw a black hole for the first time. The image, captured by the Event Horizon Telescope, showed a glowing ring of light surrounding a dark shadow, the silhouette of the supermassive black hole at the center of the galaxy M87. It was a historic moment, the culmination of years of effort by hundreds of scientists, and a triumph of observational astronomy. The image proved that event horizons exist, that black holes are real, and that we can see their shadows against the luminous matter they consume. The Event Horizon Telescope, or EHT, is not a single instrument but a network of radio telescopes scattered across the globe. By combining observations from telescopes in Hawaii, Arizona, Chile, Spain, Mexico, and Antarctica, the EHT creates a virtual telescope the size of the Earth. This technique, called Very Long Baseline Interferometry, achieves angular resolution high enough to see details as small as the event horizon of a supermassive black hole, millions of light years away. The resolution is so fine that if you pointed the EHT at the Moon, it could resolve a grapefruit sitting on the surface. The target for the first image was M87 star, the supermassive black hole at the center of the elliptical galaxy M87, located about 55 million light-years away. This black hole weighs 6.5 billion solar masses, making it one of the largest and closest supermassive black holes visible from Earth. Despite its size, the event horizon spans only about 40 billion kilometers, an angle of just 40 microarc seconds as seen from Earth. To put this in perspective, it is like trying to photograph an orange on the moon. The EHT does not capture images in visible light, but in radio waves at a wavelength of 1.3 millimeters. This wavelength was chosen because it can penetrate the dust and gas surrounding the black hole, and because it provides the best compromise between resolution and sensitivity. The observations were conducted in April 2017, when all the telescopes in the network pointed at M87 for several nights, collecting data simultaneously. Each telescope recorded petabytes of information, so much data that it could not be transmitted over the internet. Instead, hard drives were physically shipped to central processing facilities where supercomputers combined the signals. The image that emerged shows a bright ring of light, the photon ring, surrounding a dark circular shadow. The shadow is about 2.5 times larger than the event horizon itself, a prediction of general relativity. Light from the accretion disk surrounding the black hole is bent by the black hole's gravity, creating a bright ring. Some photons orbit the black hole multiple times before escaping, creating additional faint rings nested inside the main one. The shadow in the center is not the event horizon, but the photon sphere, the region where light orbits the black hole. Inside this region, all photons fall into the black hole, creating the appearance of a dark disk. The image matches the predictions of general relativity with stunning accuracy. The size of the shadow corresponds to a black hole of 6.5 billion solar masses, consistent with measurements from stellar orbits and gas dynamics. The brightness is asymmetric, brighter on one side than the other, an effect caused by the black hole's rotation. As the accretion disk spins, material on the side moving toward us is Doppler boosted, appearing brighter, while material moving away is dimmed. This asymmetry allowed scientists to determine that the black hole is rotating and to measure the direction of its spin axis. In 2022, the EHT released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Imaging Sagittarius A star was even more challenging than M87. Although it is much closer, only 26,000 light-years away, it is also much smaller, weighing just 4 million solar masses compared to M87's 6.5 billion. The event horizon is correspondingly tiny, making it a difficult target. Additionally, the material orbiting Sagittarius A star moves much faster, completing an orbit in minutes rather than weeks. This means the accretion disk changes rapidly, like trying to photograph a squirming child. To overcome these challenges, the EHT team developed new algorithms that could reconstruct a stable image from data that changed over the course of the observations. The result was another glowing ring with a dark shadow, remarkably similar to the M87 image despite the vastly different scales. Once again, the size and shape matched the predictions of general relativity, confirming that Sagittarius A star is indeed a black hole, and that it behaves as Einstein's equations predict. The success of the EHT has opened a new era in black hole imaging. Future observations will improve the resolution and sensitivity, allowing the detection of finer structures like the nested photon rings and the jets launched from the black hole. Adding more telescopes to the network, including space-based observatories, will enhance the virtual telescope even further. Scientists are also working on techniques to create movies of black holes, showing how the accretion disk evolves over time and how matter falls toward the event horizon. One of the most exciting prospects is testing general relativity in the strong field regime. The photon ring is a direct probe of spacetime geometry near the event horizon, and any deviation from Einstein's predictions would show up as changes in the ring's size or shape. So far, the observations are consistent with general relativity, but as measurements become more precise, they could reveal new physics. Some theories of quantum gravity predict small corrections to the behavior of light near black holes, effects that might be detectable with future observations. Black hole imaging also provides insight into the physics of accretion and jet formation. By comparing images at different wavelengths and at different times, scientists can study how magnetic fields thread through the accretion disk, how energy is extracted from the black hole, and how jets are launched and collimated. These processes are not yet fully understood, and black hole images provide crucial data to test theoretical models. The images of M87 and Sagittarius A star are more than scientific achievements. They are cultural milestones, visual proof that black holes exist, that they can be seen, and that they look exactly as theory predicted. For the first time, humanity has gazed into the abyss and seen it staring back, a luminous ring surrounding infinite darkness. The shadow of a black hole is the shadow of spacetime itself, the visible edge of a region from which nothing can return. And in seeing that shadow, we have reached across the cosmos to touch the most extreme objects the universe can create. Ultra-compact objects and black hole mimickers. Black holes are so strange that scientists have long wondered whether other objects might mimic their behavior without actually being black holes. These hypothetical objects, called black hole mimickers or ultra-compact objects, would be dense enough to produce similar gravitational effects, but would lack true event horizons. They represent alternative endpoints for stellar collapse or exotic states of matter that could exist in extreme conditions. While no mimickers have been definitively identified, their study sheds light on what makes black holes unique and what observational tests could distinguish them from alternatives. One class of mimickers involves modifications to general relativity itself. In some alternative theories of gravity, the event horizon never quite forms. Instead, the collapsing star approaches a black hole-like state but stops just short, creating an ultra-compact object with a surface rather than a horizon. This surface would be incredibly close to where the event horizon would have been, perhaps differing by less than a centimeter for a stellar mass object. From a distance, such an object would be indistinguishable from a black hole. It would have the same mass, the same gravitational pull, and the same effect on orbiting stars and gas. The key difference would be at the surface itself. A true black hole has no surface, only an event horizon beyond which nothing escapes. But an ultra-compact object would have a physical surface, albeit an incredibly dense and compact one. This surface could, in principle, reflect or emit radiation, producing signals that a black hole could not. For instance, if matter fell onto the surface, it might produce bursts of X-rays or gamma rays. By contrast, matter falling into a black hole simply disappears behind the event horizon, producing no surface emission. Searching for such signals is one way to test whether candidate black holes are truly black holes or something else. Another type of mimicker involves exotic matter. Some theories predict that at extremely high densities, matter could undergo phase transitions to states not found in ordinary conditions. Quark stars, for instance, are hypothetical objects where the intense pressure breaks down protons and neutrons into their constituent quarks. The resulting quark matter would be incredibly dense, possibly dense enough to mimic a black hole. Similarly, boson stars are hypothetical objects made of bosons, particles that can occupy the same quantum state, held together by gravity and self-interaction. These stars would have no event horizon but could be extremely compact. Gravastars are another proposed alternative. The term stands for gravitational vacuum star, an object where quantum effects near what would be the event horizon create a phase transition, replacing the interior with a vacuum-like state. The gravastar would have a thin shell of matter surrounding a void, with no singularity at the center. From the outside, it would look almost identical to a black hole, but it would lack an event horizon and singularity. The concept is speculative and lacks a firm theoretical foundation, but it illustrates the kinds of alternatives physicists have considered. Distinguishing black holes from mimickers is challenging. Most observational tests rely on indirect evidence: the mass of the object, its compactness, and the behavior of matter nearby. For stellar mass objects, one key test is gravitational wave signals. When two black holes merge, they produce a specific waveform that reflects the structure of spacetime near the event horizon. If the objects had surfaces, the waveform would differ slightly, particularly in the ring-down phase, when the merged object settles into a stable configuration. So far, all observed gravitational wave signals are consistent with black holes, not mimickers, but future detectors with higher sensitivity could reveal deviations. Another test involves looking for echoes in gravitational wave signals. If an object has a surface or a near-horizon structure, gravitational waves bouncing off that structure could create faint echoes following the main signal. Some researchers have claimed to detect such echoes in LIGO data, but the evidence is controversial and not widely accepted. Confirming or refuting these claims will require better data and more sensitive instruments. For supermassive black holes, one powerful test is the black hole shadow. The Event Horizon Telescope images show a dark shadow surrounded by a bright ring. This shadow is a direct consequence of the event horizon. If the object were not a black hole, but an ultra-compact star with a surface, the shadow would be smaller or absent, and the surface might emit light that fills in the dark region. The fact that M87 and Sagittarius A star show shadows consistent with black holes is strong evidence that they are indeed black holes, not mimickers. Another test involves the accretion of matter. Black holes can have accretion disks that extend down to the innermost stable circular orbit, or ISCO, a region very close to the event horizon. Below this radius, matter plunges directly into the black hole, emitting no additional radiation. For an ultra-compact object with a surface, matter would continue to radiate all the way down to the surface, producing a different spectrum of emission. By studying the X-ray spectra of accreting compact objects, astronomers can test whether they have surfaces or event horizons. Despite these tests, completely ruling out mimickers is difficult. Nature may be more creative than we imagine, and exotic objects could exist that evade current detection methods. However, the accumulated evidence strongly favors black holes. Gravitational wave observations, black hole images, and X-ray spectroscopy all point to objects with event horizons and no surfaces. If mimickers exist, they are rare and well hidden. The study of black hole mimickers is valuable not because they are likely to exist, but because they force us to question our assumptions and sharpen our tests. They remind us that extraordinary claims require extraordinary evidence, and that we should always be willing to consider alternatives. And in the end, every test that fails to find mimickers strengthens our confidence that black holes are real, that event horizons exist, and that the universe truly does contain regions from which nothing can escape. Black holes, from quantum to cosmos. We have journeyed through the full spectrum of black holes, from the smallest quantum fluctuations to the largest cosmic titans. We have seen how they form, how they evolve, and how they shape the universe around them. But the story is far from over. Black hole physics stands at the frontier of modern science, a field where new discoveries are being made every year and where the deepest mysteries of nature remain unsolved. The future promises even more remarkable insights as technology advances and our understanding deepens. One of the most exciting frontiers is the search for intermediate mass black holes, the missing link between stellar and supermassive black holes. New telescopes and gravitational wave detectors are beginning to probe the mass range where these objects should exist. The James Webb Space Telescope, with its ability to peer into the distant universe, may discover intermediate mass black holes in dwarf galaxies or ancient star clusters. LISA, the space-based gravitational wave detector planned for the 2030 S, will be sensitive to mergers involving intermediate mass black holes, potentially detecting dozens or hundreds of events over its mission lifetime. Finding these objects would solve one of the biggest puzzles in astrophysics: how supermassive black holes grew so large so quickly. Another major question is the nature of black hole singularities. General relativity predicts that singularities are inevitable, but it also breaks down at those points, producing infinite densities and infinite curvatures. A complete theory of quantum gravity is needed to understand what truly happens at the center of a black hole. Several approaches are being pursued, including string theory, loop quantum gravity, and other frameworks. These theories suggest that singularities might be replaced by quantum structures, regions where spacetime itself is granular or undergoes transitions to new states. Confirming these ideas will require both theoretical breakthroughs and new observational tests, possibly through gravitational waves or black hole imaging. The black hole information paradox also remains unresolved. Does information falling into a black hole truly disappear, or is it preserved in some subtle way? Recent developments involving quantum entanglement and holography suggest that information is not lost, but rather encoded in complex correlations that are released as the black hole evaporates. But the details are still debated, and a complete understanding will likely require a unified theory of quantum mechanics and gravity. Resolving the information paradox would have profound implications, not just for black holes, but for the nature of information, entropy, and the fundamental structure of reality. Gravitational wave astronomy is entering a golden age. Ground-based detectors are being upgraded to improve sensitivity, and new facilities are being planned. The Einstein telescope, a proposed underground detector in Europe, will be 10 times more sensitive than current instruments, capable of detecting black hole mergers from the edge of the observable universe. Cosmic Explorer, a planned detector in the United States with arms 40 kilometers long, will push sensitivity even further. Together, these instruments will detect thousands of black hole mergers per year, providing a complete census of black hole populations and enabling precision tests of general relativity. LISA will open an entirely new window, detecting low-frequency gravitational waves from supermassive black hole mergers. When galaxies collide, their central black holes eventually merge, releasing gravitational waves that LISA will detect years before the final coalescence. This early warning will allow electromagnetic telescopes to observe the events in real time, studying the environments around merging supermassive black holes and searching for light emitted during the merger. LISA will also detect extreme mass ratio in spirals, events where stellar mass black holes spiral into supermassive ones, providing exquisitely detailed maps of spacetime near supermassive black holes. Black hole imaging is also advancing rapidly. The Event Horizon Telescope network is expanding, adding new telescopes that will improve resolution and allow observations at multiple wavelengths. Future space-based observatories could join the network, creating baselines even larger than Earth's diameter. These improvements will enable the detection of finer structures like the nested photon rings and the base of jets. Scientists are also working on creating movies of black holes, tracking how the accretion disk and event horizon region evolve over minutes, hours, or days. Such movies would reveal the dynamics of matter and magnetic fields near the event horizon in unprecedented detail. One of the most ambitious goals is detecting Hawking radiation. For astrophysical black holes, the radiation is far too weak to observe directly. But future experiments might detect Hawking radiation from analog black holes created in laboratories, or from primordial black holes if they exist. Detecting Hawking radiation would confirm one of the most profound predictions of theoretical physics and provide a direct link between quantum mechanics, gravity, and thermodynamics. The search for primordial black holes continues. New surveys are scanning the sky for gravitational microlensing events that could reveal these ancient objects. If primordial black holes make up even a fraction of dark matter, they should occasionally pass in front of distant stars, causing brief brightening events. Advanced surveys like the Vera Rubin Observatory will monitor billions of stars simultaneously, providing unprecedented sensitivity to such events. Gravitational wave detectors are also searching for signatures of primordial black hole mergers, which might have different properties than mergers of stellar black holes. There is also growing interest in the connection between black holes and cosmology. Black holes are not isolated objects, but part of the cosmic web, influenced by and influencing the large-scale structure of the universe. Understanding how black holes grow, merge, and interact over cosmic time requires combining observations from multiple wavelengths and simulations of galaxy formation and evolution. Future missions will trace the history of black holes from the earliest moments of the universe to the present day, revealing how they shaped the cosmos we see today. Finally, black holes may hold the key to understanding the ultimate fate of the universe. In the far future, after stars have burned out and galaxies have dispersed, black holes will be the last massive objects remaining. They will slowly evaporate through Hawking radiation, a process that will take unimaginably long, but is ultimately inevitable. Understanding this process and what happens when the last black hole evaporates is essential to understanding the end of time itself. Some theories suggest that the universe will end in a state of maximum entropy, a cold, dilute soup of particles with no structure or complexity. Others propose more exotic possibilities, including quantum transitions or cyclic universes, where new Big Bangs emerge from the ashes of old ones. Black holes have come a long way from mathematical curiosities to observed objects, from hypothetical endpoints of stellar collapse to cosmic laboratories testing the limits of physics. Every new observation reveals something unexpected. Every new theory opens new questions. The journey through every type of black hole is a journey through the extremes of nature, from the smallest scales of quantum mechanics to the largest scales of cosmology. And as we stand on the threshold of new discoveries, one thing is clear: black holes will continue to surprise, challenge, and inspire us for generations to come. Supermassive black hole binaries. When two galaxies collide, their stars rarely crash into each other. Space is vast, and the distances between stars are so large that most pass by harmlessly, their orbits scrambled by gravity, but their physical integrity intact. But at the centers of these galaxies, where supermassive black holes reign, a different fate awaits. The two black holes, each weighing millions or billions of solar masses, begin a slow gravitational dance that will end billions of years later in one of the most energetic events the universe can produce: a supermassive black hole merger. The process begins when two galaxies approach each other, drawn together by gravity over hundreds of millions of years. As they collide, gas clouds smash into each other, triggering bursts of star formation that light up the galaxies like cosmic fireworks. The stars themselves pass through relatively unscathed, but the structure of both galaxies is transformed. Spiral arms are torn apart, disks are disrupted, and eventually the two galaxies merge into a single, larger, elliptical galaxy. Throughout this chaos, the two supermassive black holes at the galactic centers sink toward the middle of the newly formed galaxy, pulled by a process called dynamical friction. Dynamical friction occurs when the massive black hole moves through a sea of stars and dark matter. As it passes, it gravitationally attracts nearby objects, pulling them along. These objects, in turn, exert a gravitational drag on the black hole, slowing it down and causing it to lose orbital energy. Over millions of years, both black holes spiral inward, their orbits shrinking until they are separated by just a few light years. At this point, they form a bound binary system, two supermassive black holes orbiting each other at the heart of the merged galaxy. But here the process stalls, and we encounter what is known as the final parsec problem. When the black holes are separated by about 1 parsec, roughly 3 light years, dynamical friction becomes inefficient. Most of the stars that could have absorbed energy from the binary have already been ejected or consumed, and there are not enough remaining to continue driving the black holes together. According to simple calculations, the binary should stall at this separation, orbiting each other indefinitely without ever merging. Yet observations suggest that supermassive black hole mergers do occur because we see the aftermath. merged galaxies with single central black holes, and occasional candidates for pre-merger binaries. Something must be bridging the final parsec. Several mechanisms have been proposed. One possibility is that gas plays a crucial role. If the galaxy contains enough cold gas, it can form a circumbinary disk, a rotating disk of material surrounding both black holes. As the black holes orbit, they gravitationally interact with this disk, transferring angular momentum and energy. This interaction can drive the black holes closer together, shrinking their orbit even when dynamical friction has become ineffective. Another possibility involves three-body interactions. If a third massive object, such as another black hole or a dense star cluster, interacts with the binary, it can carry away energy and angular momentum, nudging the pair closer together. Once the black holes get close enough, within about 1/100th of a parsec, gravitational wave emission takes over. At this separation, the black holes are orbiting each other rapidly enough that they generate strong gravitational waves, ripples in spacetime that carry energy away from the system. As they radiate gravitational waves, the black holes lose energy and spiral inward faster and faster. The process accelerates exponentially. What took millions of years to shrink from light years to 1/100th of a parsec takes only thousands of years to shrink to the final merger. In the last hours before collision, the black holes are orbiting each other at a significant fraction of the speed of light, releasing gravitational waves so powerful that they shake the fabric of space-time across the universe. The merger itself is cataclysmic. When the two event horizons touch, they immediately combine into a single, larger event horizon. The merged black hole is initially distorted, elongated by the collision, and it vibrates like a struck bell, a phase called ring-down. During this phase, the black hole emits gravitational waves at specific frequencies determined by its mass and spin, gradually settling into a stable spherical configuration. The entire process from the final inspiral to the ring-down releases more energy than all the stars in the observable universe emit over the same time period. Most of this energy is carried away by gravitational waves, but some can be released as electromagnetic radiation if gas is present. Detecting these mergers is one of the primary goals of LISA, the Laser Interferometer Space Antenna. Ground-based detectors like LIGO are sensitive to stellar mass black hole mergers, which produce high-frequency gravitational waves. But supermassive black hole mergers produce low-frequency waves, with periods ranging from hours to months, far below what ground-based detectors can observe. LISA, operating in space and consisting of 3 spacecraft separated by millions of kilometers, will be perfectly positioned to detect these events. It will observe supermassive black hole mergers from across the universe, providing early warning months or years before the final coalescence. This early warning is revolutionary. For the first time, astronomers will know when and where a merger is about to occur, allowing them to point telescopes at the source and search for electromagnetic counterparts. If gas is present around the merging black holes, the collision could produce flares of light, from radio waves to X-rays, as the gas is heated, compressed, and ejected. Observing a merger in both gravitational waves and light would provide unprecedented insight into the physics of accretion, the environments around supermassive black holes, and the behavior of matter under extreme gravity. Supermassive black hole binaries also have profound effects on their host galaxies. As the black holes orbit, they can eject stars through gravitational slingshots, carving out a core of lower stellar density at the galactic center. They can also drive powerful outflows of gas, clearing the central regions of material that would otherwise form new stars. These effects may help explain why some elliptical galaxies have unusually low stellar densities in their cores, and why star formation is suppressed in certain massive galaxies. Perhaps the most intriguing possibility is the existence of recoiling black holes. When 2 black holes merge, the gravitational waves they emit can be slightly asymmetric, producing a net momentum in one direction. This recoil, or kick, can be strong enough to eject the merged black hole from the galactic center, sending it wandering through the galaxy, or even ejecting it into intergalactic space. The kick velocity depends on the masses and spins of the original black holes, and can reach thousands of kilometers per second. While direct observations of recoiling supermassive black holes are rare, a few candidates have been identified, including quasars with unusual velocities and galaxies with off-center active nuclei. Supermassive black hole binaries represent the ultimate stage in galaxy evolution, the cosmic unions that mark the end of galactic mergers and the beginning of new, larger structures. They are among the most powerful events in the universe, releasing energies that dwarf anything else we observe. And in the coming decades, as LISA and other instruments come online, we will witness these mergers for the first time, hearing the deepest notes in the cosmic symphony, and learning how the largest black holes in the universe come together. Tidal disruption events. Most stars keep a safe distance from black holes, orbiting at distances where gravity is strong but not catastrophic. But occasionally a star wanders too close. Perhaps its orbit was perturbed by a gravitational encounter with another star, or perhaps it was on an elliptical path that brought it near the galactic center. Whatever the reason, the star crosses an invisible threshold called the tidal radius, and in that instant its fate is sealed. The black hole's gravity begins to pull harder on the near side of the star than the far side, stretching it like taffy. Within hours, the star is torn apart in one of the most violent processes in astrophysics, a tidal disruption event. The physics of tidal disruption is brutal and elegant. Gravity weakens with distance according to an inverse square law, meaning that an object closer to a black hole experiences stronger pull than an object farther away. For small objects like planets or asteroids, this difference is negligible. But for a star, which can be millions of kilometers across, the difference becomes significant. The near side of the star is pulled inward with far more force than the far side, creating a tidal force that stretches the star along the radial direction and compresses it perpendicular to that direction. If the tidal force exceeds the star's self-gravity, which holds it together, the star is pulled apart. The tidal radius depends on the masses and sizes of both the black hole and the star. For a supermassive black hole weighing 1 million solar masses and a Sun-like star, the tidal radius is about 100 million kilometers, roughly the distance from the Sun to Earth. For more massive black holes, the tidal radius is farther out. Paradoxically, this means that stars are safer around the largest black holes. A black hole weighing 1 billion solar masses has such a large event horizon that the tidal radius lies inside it. A star approaching such a black hole would cross the event horizon intact, disappearing without being disrupted. Only around intermediate and moderately massive supermassive black holes, those weighing between a few 100,000 and a few 100 million solar masses, can tidal disruption events occur outside the event horizon where they can be observed. When a star is disrupted, about half of its material remains bound to the black hole, falling inward to form an accretion disk. The other half is ejected at high speed, carrying away energy and momentum. The bound material does not fall directly into the black hole. Instead, it retains some of its original orbital angular momentum, causing it to spiral inward gradually. This process takes weeks to months, during which the infalling gas heats up through friction and compression, emitting intense radiation. The peak luminosity of a tidal disruption event can rival or exceed that of an entire galaxy, making them visible across cosmological distances. The light curve of a tidal disruption event has a characteristic shape. It rises sharply as the star is torn apart and the debris begins to accrete, reaching peak brightness within days or weeks. Then it declines gradually, fading over months to years as the supply of gas is exhausted. The exact shape of the light curve depends on the properties of the star, the mass of the black hole, and the geometry of the encounter. By studying these light curves, astronomers can learn about the black holes doing the disrupting and the stars being destroyed. Tidal disruption events were first predicted theoretically in the 1970s and 1980s, but observing them proved difficult. They are rare, occurring perhaps once every 10,000 to 100,000 years per galaxy. With billions of galaxies in the observable universe, dozens should be happening at any given moment. But finding them requires monitoring vast numbers of galaxies and catching the transient brightening. The advent of large sky surveys in the 2000s and 2010s changed everything. Telescopes like the Zwicky Transient Facility, Pan-STARRS, and the All-Sky Automated Survey for Supernova began scanning huge swaths of sky every night, searching for anything that changed. Supernovae, variable stars, and other transients lit up the data, and among them, tidal disruption events began to appear. One of the most famous examples is Quasars 15 LH, detected in 2015 by the All-Sky Automated Survey for Supernovae. It was initially classified as an extraordinarily luminous supernova, the brightest ever observed. But as astronomers studied it more closely, they realized it did not fit the supernova model. The light curve was wrong, the spectrum was unusual, and the host galaxy showed signs of harboring a supermassive black hole. The leading explanation is that Quasars 15 LH was a tidal disruption event, possibly involving an unusually massive star or an extreme encounter geometry. The event released as much energy as hundreds of typical supernovae, demonstrating the sheer power of tidal disruption. Another remarkable case is at 2019 DSG, a tidal disruption event that coincided with the detection of a high-energy neutrino. Neutrinos are nearly massless particles that rarely interact with matter, making them difficult to detect but valuable as messengers from extreme environments. The neutrino detected by the IceCube Observatory in Antarctica appeared to come from the direction of AT 2019 DSG, suggesting that tidal disruption events can accelerate particles to ultra-high energies and produce neutrinos. This was the first time a neutrino had been associated with a tidal disruption event, opening a new window onto the physics of these events. Tidal disruption events also provide a unique way to study otherwise dormant supermassive black holes. Most supermassive black holes are not actively feeding, so they emit little radiation and are difficult to detect. But when a tidal disruption event occurs, the black hole suddenly flares into visibility, revealing its presence and properties. By cataloguing tidal disruption events across many galaxies, astronomers can estimate the population of supermassive black holes, measure their masses, and study how they interact with their environments. The disrupted stars themselves can be anything from sun-like stars to red giants to white dwarfs. The type of star affects the event's observational characteristics. Red giants, with their extended atmospheres, can be disrupted at larger distances, while compact white dwarfs can survive closer approaches. Some tidal disruption events involve exotic scenarios, such as a star on a highly eccentric orbit that is partially disrupted on one pass, survives and returns for another encounter. These repeated partial disruptions create complex light curves that can be used to probe the star's structure and the black hole's environment. Tidal disruption events are more than violent spectacles. They are cosmic laboratories where we can study the behavior of matter under extreme tidal forces, the formation of accretion disks, and the physics of jets and outflows. They reveal the hidden population of supermassive black holes lurking in galactic centers and provide glimpses of the dynamic processes that govern the interactions between stars and black holes. And as sky surveys become more powerful, detecting hundreds or thousands of tidal disruption events, we will gain a statistical understanding of these events, learning how often they occur, what types of stars are most vulnerable, and how black holes respond to sudden influxes of stellar material.